Hello, everyone, and welcome to the Lifelong Learning and Personalization in Long-Term Human-Brain Interaction workshop. This is the fourth year that we're doing this for making a leap from the traditional approaches of human-brain interaction towards adaptable robots of the future. So what is lifelong learning? Let's start with that, right? So it's also known as continual learning. It's learning from the data, from that you see, you experience with the robots, and continue learning and scaling your model or adapting your model so that you can have a model that has updated parameters, can learn new facts, and also retain the previously learned facts, so it doesn't have this what is called a catastrophic forgetting, so that you can actually perform as well as you were doing previously before you start learning new data. And why do we need this, right? So we have these long-term interactions, robots in the wild. You can't have a robot that has a very fixed set of behaviors or fixed set of skills that doesn't learn from you, because imagine talking to the robot every day and it just keeps on saying the same things. It's not going to be, fun to talk to. Or if you have a robot that's in your house and it needs to learn from you, it needs to learn what are the certain skills and so on, or adapt and generalize and personalize so that you can have robots that are useful in these long-term interactions. This year, we're focusing on open world learning. And this means when you put the robots in the wild, there's going to be objects or users or things that are new. And it needs to detect these new things and scale the model to incrementally learn those things so you can recognize them in the future. And you can see a very well connection with the lifelong learning, right? And who am I? I'm Bahar Irfan. I'm the coordinator and founder of this workshop since 2021. And I'm a postdoc and a digital features fellow at KTH Royal Institute of Technology. And my work focuses on creating personal robots that can continue to learn and adapt to help everyone in their everyday lives. My current work, I'm working on lifelong learning in large language models so that we can provide personalized conversations in particular to older adults, so in their daily lives, so we can provide social and emotional support. Previously, I was at Avinox. I was working on customized solutions for industrial robots, virtual reality, and smart buffets. And before that, I was at Disney Research, creating adaptable dialogues using emotions with the virtual agent that can understand your emotions, has its own emotions, and adapt accordingly. I did my PhD in University of Plymouth and SoftBank Robotics Europe in a Mary Scholastic Curie project, where I worked on multimodal personalization from open world user recognition and personalization for cardiac rehabilitation robot, as well as task-oriented dialogue for a barista setting, so that we can personalize these interactions and provide great experiences. And I'm organizing this workshop with fantastic people. And throughout the many years, we did the same exchange, but I am super happy with this team as well. So first of all, we have Mariacarla Staffa, and she's an assistant professor in human-robot interaction, artificial intelligence, and cognitive robotics at the Department of Science and Technologies at the University of Naples, Partenopei, in Italy. She's the coordinator of the Brain Laboratory, the Bio-Inspired Robotics and Artificial Intelligence Networking Lab, there, and working on cognitive robotics, AI, and social and assistive robotics. She's mainly interested in exploring computational neuroscience and cognitive robotics to generate innovative strategies and solutions for scientific problems and technological limitations. She has a PhD and an MSc from University of Federico too. And next up, we have Andreea Bobu. She's a research scientist at Boston Dynamics AI Institute and upcoming assistant professor at MIT. In her research, she studies algorithmic human-robot interaction with a focus on how robots and humans efficiently arrive at shared representations of their tasks for more seamless and reliable interaction. She obtained her PhD in electrical engineering and computer science at UC Berkeley with Anka Dragan, and she received a bachelor's in computer science and engineering at MIT. And finally, we have Nikhil Churamani over there. He's a postdoc researcher at the Effective Intelligence and Robotics FR Lab at the Department of Computer Science and Technology at University of Cambridge. His research interests include effective robotics, continual learning, federated learning, human in the loop, reinforcement learning, and HRI. His current research focuses on federated continual learning of socially appropriate robot behaviors in human-centered environments. So this workshop, as I said, has been going on since 2021. And you can actually watch all of these previous workshops as well as this after we finish for the talks and debates. We've been trying to have both industry and academia present in this workshop because we need these collaborations to be able to build robots, adaptable robots of the future that can actually be present in our day-to-day lives. And this workshop actually started back in 2019 as a personalization long-term interaction workshop at HRI. It was the first time I found this workshop. And then it evolved along with the organizers in the lifelong learning for long-term HRI workshop at Roman into this LEAP-HRI. And we'll be having 70 to 100 participants per year, which is fantastic. And it actually shows how much important it is for HRI to have lifelong learning and personalization. So I'm going to give a brief overview of the program. We decided to have both lifelong learning and personalization aspects. I'm going to start with Sonia Chernova on personalized robot assistance in the home, and with Andreea chairing. I'm going to give her the floor in a bit. And then we're going to go on to our 6 accepted papers. They're fantastic. I am very excited about all of them. The whole workshop I'm actually very excited about, such as reinforcement learning in assisted robotics, and as well as prosody. That will be, we start with first. And then we relax, take a coffee break, catch up, kind of have these networking event. We don't have a poster session because it's like I didn't want to have people fixing a place. You need to be moving around, talk to everyone. This is all about networking. I hope you get to experience that. And back in 10:30, we're coming back with Silvia Rossi. She's going to be remote, and Mariacarla is going to chair that session. So she's going to talk about proactive behavior and theory of mind. And we have the next session with Nikhil as well, sharing when federated learning, augmented reality, learning from demonstration, as well as the long-term task learning. Finally, we have the debate. Tony moderating it. I'm going to be the chair. Georgia and Georgia Shavatsky is going and Sidar Srinivasa is going to be attending us online, and Haywan Park and Maya Matarak is going to be here. The topic of the debate is still going to be a surprise, so stay tuned. And then we will follow that up with a breakout session where you're going to talk about the debate topic and what are the discussions that went on throughout the debate, and introduce yourself, very short, 1 minute introduction, and then we're going to have this group session and talk about all of this in 4 to 5 people groups. Then finally, Mariacarla is going to conclude the workshop, and we're going to be letting you go back to HRI and explore other areas of HRI. We hope you enjoy this workshop. We put a lot of effort in it, but I think it's worth it. I think that this is something we need to keep on doing to actually build these robots, the adaptable robots of the future. And I hope you agree with me as well. So I'm gonna switch back to Andreea to introduce our first keynote. Thank you.
Well, it is my great pleasure to introduce our first keynote speaker of the day, Professor Sonia Chernova. Sonia is an associate professor in the College of Computing at Georgia Tech. She directs the Robot Autonomy and Interactive Learning, or RAIL Lab, where her research focus is on the development of intelligent and interactive autonomous systems. Professor Chernova's contribution spans robotics and artificial intelligence, including semantic reasoning, adaptive autonomy, human-robot interaction, and explainable AI. She also leads the NSF AI Institute for Collaborative Assistance and Responsive Interaction for Networked Groups, or AI Caring, whose mission is to develop collaborative AI systems that help support independent home life for older adults experiencing cognitive decline. So please, let's welcome Sonia. And take it away. Nikhil, can you help me with the PowerPoint? Yeah.
Thanks for the great intro. Thank you for the invitation to be here and for coming. I'm like super, super excited to be here. So when I got invited to come speak, I started thinking about robots. I was trying to think about long-term interaction and the personalization of long-term interaction for robotic systems. I'm really motivated by homes personally. I think it's the ultimate sort of robotics challenge because of the diversity, the challenges, the kind of really unique aspects of every user, every home that make robotics really difficult as an application in this domain. Are we now good? Looks like we're good. Okay. And so okay. I will one way make it work. It's gonna be fine. And so sorry, I'll stay next to the mic. This diversity of human homes to me presents a really interesting challenge. Well, it presents an interesting challenge for all of us as a community, I think, in terms of getting robots out into the world and working with people. And so today, I think lifelong learning is an absolutely critical component. I'm not going to talk about catastrophic forgetting. I think other people probably will today, and I think it's a really important topic. I want to talk about personalization. And what does personalization look like when you have this robot with you for a very, very long time? And in particular, the question I want to explore is how can home robots provide personalized assistance in an unobtrusive way? And I've crafted this with two particular sort of words in mind. One is this personalization, by which I mean adaptation to the user's unique needs and habits and their environment and all of the things that come with personalization. But the other element I want to talk about is this unobtrusiveness. If you have a robot with you for the long haul, like a month, 2 months, a year, 2 years, what do you want that interaction to look like? And I think we have a lot of people coming into the HRI community recently. LLMs are big, language is big, and there's this tendency to say, I want to talk to the robot. I want to tell it what to do and it'll do it. And I think that it's actually going to be a little bit exhausting in the long term, right? If you have to tell the robot every single thing you want it to do, everything you want it to pick up and to bring, and I think it becomes a little bit overwhelming. And so I want to talk about what does minimal effort look like, and how can a robot personalize itself with minimal effort, especially when we start to think about these longitudinal scenarios. And so, again, there's been lots and lots of work. So I've already prefaced this slide a little bit. There's been lots and lots of work on getting robots to do things. A lot of it more recently and all over the history, but especially more recently is focused on language driven, right? Set the table, get me a Pepsi, put the Pepsi away, stack some things. And that's really powerful, and we need that. There's no question. We absolutely need language-driven, tasking. But since in this workshop, we're looking at that longitudinal element, I want to talk about what are the alternatives? What are other ways that we can interact with robots? And so there's this other subfield that's really interested me recently on proactive robot assistance, on knowing that the user needs something and providing assistance before being asked. And so that seems like a really interesting thing to explore in the context of longitudinal behavior. And there's lots and lots of work on that in the community as well. I would say one thing I'll point out about the images from these papers is that it's almost always tabletop scenarios, right? So you have a overhead camera, you have a robot arm, and you have a human. You're tracking the human's movement. Think like a surgery, like when the surgeon says scalpel, right? And someone hands them, the nurse hands them the scalpel. That's the kind of scenarios that are being explored because a lot of it is manufacturing driven and so on. And there's, again, a huge need for that, but it doesn't quite work in the longitudinal scenario in the home setting because you're not going to have a single table. You're not going to have that many cameras or instrumentation. It just doesn't quite necessarily fit with what we want to do. And so what I want to do is talk about two different threads of work that focus on this idea that repetitive, predictable, low stakes tasks, particularly in the home, should be automated with minimal human effort required for the personalization. I want it to be personalized, but I, as a user, want to be super lazy and not be very engaged with the robot in order to make this sort of not be exhausting to the user and participants. And so let me start. Again, I'm going to talk about two threads of work. Let me start with one where we just talk this through in the task of putting away groceries, which is a mundane task. We do it very often. It's fairly low stakes. It's something that's also quite personal to different people. And again, another connected research community here is object rearrangement, right? There's a lot of papers recently on object rearrangement, scene rearrangement, lots of really interesting research there. A lot of them focus on starting out with a pretty empty environment. Here's a bunch of stuff. How would you arrange it? Okay. But we want to talk about a particular user and deploy a robot in their home. And the thing about it is that most of the time, my home, actually 99.99999% of the time, my house doesn't look empty, right? I already have stuff in it. And so when I buy more stuff, I want it to go somewhere, but I need it to fit with the things I already have. And, you know, usually when you're buying groceries, your fridge may be not quite as full. It's really hard to find a half full fridge in stock images. But anyway, but the idea is that you have already certain items in the environment. And what I want to argue is that the objects themselves, right, and their placement provide hints, really valuable information about the user's preferences, about their personal style of arranging their space. And that information can be directly kind of obtained from the environment and inferred from observations without needing specific tasking from the user. I should be able to come to your house. It might take me a little, it might be not the most efficient the first time I do it, but if you give me groceries, I can probably put them away in something that's not super jarring to you because I can use semantic context to do so. And so let me walk you through a little bit, and people should come in and sit down and not stand. That's totally fine. Registration's taking a really long time. So let me talk through how we've done it. And one, this is an ongoing project for us where we're really interested in how far can we push this idea. So we started with, we went and collected 38 different categories of objects, household objects. And then it doesn't, you know, lots and lots of different objects. There's some food items, some cleaning items, some utensils, all kinds of stuff. And we wanted to replicate how different people might group them. And we have crowdsourced now different groupings, but at the time we said, okay, but there's like lots of people have already done this. So we looked at WordNet and said, how does WordNet cluster things? Then we looked at AffordanceNet and others. We grouped things by affordances, you know. We grouped things. We went to Walmart and looked at their product categories and grouped by their categories. And then we also made one called One of Everything, where we like, hey, you know, sometimes you want to pack a lunch, for example, for your 3 children maybe, and you need to do that. And they each need, and it's a very different grouping. And so the idea here is that not so much the grouping itself that matters. And one thing is that they're all slightly different. You know, there's pokey, sharp things versus scoopy things. You know, utensils of a certain kind, Walmart considers that go together versus WordNet considers go together. But the idea is that there's diversity here. So my note here is that the individual groupings themselves, it's not that I'm assuming that people in someone's house, you should group things by the WordNet categorizations and that's how you should live. No, like that's not reasonable. All I'm saying is these are just very diverse personas. Think about that. More diverse needs. And I just want to be able to train a model. And if I can train a model that can learn all of these diverse categories sufficiently, then I feel like I can sort of cover most people, right? And that's kind of all I'm trying to claim here. And so we just wanted to be able to sample diversity without having to justify different personalities. And so how do we do that? What do we do? So now we have all these objects. We have different categories of objects when we do. And so now we take an environment and let's put this into practice. How do we actually just use semantic context to place new objects into it? So we take some sort of new environment. We take the objects that we want to place into it. And we encode all of them using semantic knowledge. In this case, we're not using any of the ones we used to create categories. We're using, you can use ConceptNet, you can use BERT, you can use a number of other representations where, and this is an example with ConceptNet, where we encode each of those elements, we encode where they're located. You also have an index so that you can actually have your model be able to support multiple instances of the same thing. This is very important if you have multiple apples and you want to give each one to each of your children, things like that. So you basically train a transformer that learns an embedding space about how the relationship and the clustering between these objects. And what it enables you to do is to figure out that based on this person's preference of how they group objects, these are the likely places to put, you know, a new bowl, a bottle of water, some chips, and an orange. And you can do this over and over. This is one just quick diagram, but you could do this over and over in lots and lots of different scenarios with different styles of groupings. And if you look at this, at the performance of this across different tasks, so this is a quick result on benchmarking. One thing we looked at is, of course, large language models. At the time that this paper was done, it was still GPT-3. And we said, okay, well, LLMs can sort of do this, and they can, and I think GPT-4 is better at it, but not necessarily equally. They're not equally good at all types of clustering. There's a baseline from Abdo et al. That also can do this for most categories reasonably well. And this is our transformer-based architecture that's using this embedding space. And it can do really well across all 4 categories, sort of competing with Abdo for objects that's seen before. Now, the thing about doing this longitudinally that's critical is that you have to do this not only for objects you've seen before, but for objects the robot's never seen, like categories of objects it's never seen. And so the idea that we're using this some sort of semantic knowledge to generate the encoding is really critical here, because now we can do this. Now Abdo et al. Falls out. GPT can still do it. Doesn't care if it's seen an unseen object. But certain other baselines in terms of machine learning start to fall away as baselines, because they're assuming that you sort of have a closed set of objects. And so as we design for systems that we intend to use for a long time, we have to be able to generalize to objects the robot's never seen. So this is kind of a quick result to show that our model can do that. Pretty high accuracy. So in this particular project, we did have just these 4 different types of clusters. Our recent work that I don't have results for quite yet, but should have next week maybe, is now personalizing to arbitrary personal styles, and we're working towards that. But the cool thing to me in this one little project is the takeaway that what are we doing here? We're taking personal. What the big takeaway here is that we've been able to personalize and to match with very high accuracy what somebody wants, without them telling us what objects they have, what objects they're going to plan to have in the future, without giving you instructions, without language, without demonstrations, and so on. And the cool thing is, we can do this with putting away groceries, but it also applies to putting away the dishes. It also applies to putting away the laundry. There's lots and lots of rearrangement tasks in household settings that sort of generalize to this idea. And to me, this is just the beginning. There's a lot of other people working on semantic rearrangement, but I'm really, really curious how far we can push this idea of like minimal interaction with the user. And I realize I'm standing at HRI, and I'll have a slide about that at the end. But I think that leaves us to ask questions at the important parts. How far can you go without bothering your user, and then use your sort of social capital that's left over to ask the really important queries for really high uncertainty objects that the robot's really confused about. And so going back to this idea of more generally of how home robots can provide personalized assistance, that was just kind of a small example, right? So we can put away groceries, great. But how do we do this in a bigger scale, and in a full household scale potentially, right? And I've mentioned already proactive assistance, and wanting to move there. Quick example kind of to help motivate that. So I would say that most work in robotics focuses on what maybe I would we never usually use this term, but I would say it's reactive assistance, right? The user requests something and then has to wait while the robot does the thing. Now here's a quick video from Google that we've probably all seen of say can, right? And so this is a really simple task of just picking up a can, but I'm sitting here like sort of waiting. And if we have a more complex task, people will start to sort of get impatient. It's faster for me to go get my can of soda than to wait for the robot. And that's great. That's just fetching something, but the more complex task for the next, foreseeable future, robots are going to be a little bit slow. And that's okay. We can plan for that. And so I think makes sort of the case, not only in the surgical case for hand me the scalpel of type of proactive assistance, but also in a household setting, in a longitudinal setting. How do you look at the fact that the robot is a little bit slow? Can it learn what the user needs and kind of personalize its behavior to be, assistive in a proactive way, so that it fetches your drink, it fetches, cleans up, it brings out your cereal or whatever else before you even ask. And again, this is not, I don't claim to have made this insight on my own. There's lots of work in the HRI community from past works with older adults, with, for example, in independent living facilities. So other sites where they test how users interact with robotic technologies and what they prefer, and time again, when you look at this longitudinal setting, people prefer.
You're gonna have to be about a hand length or closer, preferably.
Okay, you guys hear me? No? Yes?
I would say just the closer, the less feedback you get. So I think just closer. I know it's scary. And you don't.
All right. There you go.
Yeah.
You're gonna be really loud.
That's the goal.
Okay. Sorry,
right.
I didn't know I was not being loud enough.
Better on Zoom as well.
Yeah. Apologies, guys. Yell at me if I'm not loud enough. I will now not yell at you. I'm permanently yelling at you. Okay. All right.
Yeah. Sorry for the interruption, but we're last minute scramble. I thought it turned it off.
This one. All right, you're good.
Where'd that go?
No, it's fine. All right. If anybody has trouble hearing me from this point on, let me know. Okay, great. So what do we want to do? Back to robots, longitudinal assistance and all that. We want, what I would argue is we want longitudinal proactive robot assistance, which means that taking proactive assistance and making it, so yeah, it has to be proactive. It has to be longitudinal. So not just like micro actions. Oh, I'm going to grab a screwdriver. Let me get the screws, but like long-term, and also going beyond the one table to an entire house.
So I am gonna have to. I know that. So for a second, I'm gonna turn the room back down. I'm gonna go get another speaker, and then carry on. But
Don't use the mic.
not the way you work. You have to use the mic so the Zoom people hear you, but it's not gonna come through the room.
Okay.
It's just gonna go to Zoom.
All right. On the other hand, this is a really good example of proactive assistance that I didn't know I needed, but is needed, right? Okay, so this is what we want. Let's talk about it for a few more seconds. We'll take another break. So the goal is to have robots actually assist and really take this. And how do you do that? So when we started this project, we had this idea, okay, we want to help around the house. This is going to be great, but the technical logistics sort of start to kick in. Do I run activity recognition? No, all the time. Do I like watch the person nonstop in every room of the house? This becomes a little bit problematic. Activity recognition actually is, really hard in the wild, right? We're not going to get accuracy past the top 10 most common activities. And even that accuracy is going to be around 85%. And human behavior is very diverse. Like there's all these kinds of challenges. So how do I develop a robot that can provide a system, can learn human routines, anticipate their needs ahead of time, like minutes ahead of time, and go and fetch stuff? Okay, is this too much? And we said, okay, well, what about just objects? Object tracking is really good and actually super privacy preserving. And so if I can build semantic scene graphs of the environment over time, at one time step, another time step, another time step, can I predict what the user will do with objects without really knowing activity recognition? Like there's all kinds of limitations. You don't understand necessarily their activities, but you can provide help. And so I'll go through this fairly quickly. Happy to talk about this offline, but it turns out, yes, you can do this. You can take time. You can take a semantic scene graph at a particular time point, and you can use a generative graph neural network to predict the scene graph at some delta into the future, right? So, and you can change that delta. You can look 10 minutes out, 5 minutes out, 30 minutes out. You can see what does the environment look like. And actually, again, you don't know what the underlying activity is. How far can we go if we don't know that? There's a model for this. Yay. We all love networks. We create a data set. There is no data set for longitudinal behavior that involves object tracking. There's one for activity tracking, but not for the objects being used. So we went and created one. If you ever need one for routine behaviors that representing different types of households, a household where someone leaves during the day. So vertically, the rows are days, and the x-axis is time. And so these are two different households. We have lots of different households. So for example, this person like showers in the morning as opposed to at night, sometimes eats breakfast, watches TV a lot, and so on, right? We crowdsourced this. This is what we got. And it turns out that all you do is use objects, nothing else, on a fairly complex and very difficult to predict data set. You get an interesting result. So there's a bunch of objects in the world that no one touches, like the lamp, and you want the robot to learn to leave the lamp alone, like don't carry it anywhere. And then there's a bunch of objects that are used, and you want to anticipate their correct usage. And if you're not sure, just leave it be, right? And so out of the unused objects, over 99% of the time, the robot's like, yeah, okay, that's cool. I didn't use it that day. And then for the objects the person used, 38% was correctly predicted where it would be. And then 57% of the time, the robot left it alone. And that's because of the variability of the human behavior, right? Sometimes I want cereal and sometimes I want a granola bar. Sometimes we actually did try to model that level of variability. And when it's a 50-50, in our model, we decided not to try to make an error and just leave it alone. And so we're sort of doing that because there's no interaction here. Very, very hard to predict. But I'm really, really happy that the things that you don't want to do, like take someone's keys and put them somewhere random right before they're planning to leave, we're really not doing that, right? And that's the category you want to minimize. And I was really happy to see the model do that. And so all this you can do with just objects, and that was really cool. And so then we went on and said, well, what if we did have at least some semblance? Like, what if we had activity recognition like 2%, like 50% of the time, 25% of the time, 75% of the time? Or what if we could ask the user things? And so we built another model, and in order to keep the session interactive, I'm going to go through it very, very quickly, but we actually do have a little bit of activity recognition. We do have the robot asking what the user might want to do. And there's another algorithm, an extension of that earlier model called Slate Pro that can incorporate these types of information as well as others. And I'm going to skip through all the transformer details. Yes, we encode stuff. Create a more complicated data set yet even more. It's called Homer Plus. Really encourage you to check it out. We've had other people use it. If you are looking for like being able to simulate lots and lots and lots of longitudinal diverse behavior that fits different personalities now with different objects, we have that. And what we find is that this is our original baseline, our earlier work. We changed the model a little bit. We added a little bit more history to object tracking, and that led to a boost. And then we get further and further boosts, but not too much of a drop off if we have activity recognition. So this is just 25% of the time you have activity recognition, the model doesn't do much. If you have 100% of the time activity recognition, yeah, it starts to do a lot better. It's a little bit unrealistic, but you sort of see a gradual increase. And then the other thing this model does is the further out you sample, it's still, the performance actually stays stable. So the F1 scores here is 0.59 as far as like long horizon planning in the longitudinal sense. And so we've been really excited. We can also ask people for help. So I'll show a quick video. I'm going to come back to this video when I take questions. We actually did a full stack implementation of this using lots of libraries from other people, Sparse Inst for object tracking, Hydra out of MIT for the scene graphs modeling. So this is a full stack implementation on the robot that could actually watch the environment, build the scene graphs, and do this over time. So I'll play this video in a minute. But the slide I want to end on first is, here I am at HRI at a workshop telling you that I want robots to be unobtrusive. And in my examples, we had very, very minimal interaction. And that's not to say that there shouldn't be interaction in, like, HRIs is a critical research area, and I believe that. But I also think that more interaction is not always the answer. And especially just for this really longitudinal case, I think we have to really carefully think about when interaction should happen and when it shouldn't. And this was a little bit extreme. We went for, what if we barely talk? What happens? How much can you push personalization? And then maybe now we start to add personalization, interaction, verbal interaction to deconflict things. And so quick thanks to Kartik Ramachandruni and Maithili Patel, whose work I presented. They're the stars behind this. It's their papers. And do we have a minute for questions? Couple minutes for questions? 5 minutes for questions. I was going off of your cues. Great. So I'll leave the video up and then we can take questions.
Hello? Okay. All right. Well, thank you for the great talk. Do we have any questions from the audience? Yes. Let's go with the person in the corner.
Really great work, really interesting. Have you looked at like object movement in multi-user households? So I'm thinking about like me proactively moving my husband's keys and him blaming the robot for doing the thing. Because like when we live in multi-person households, we do try to help each other, but sometimes it's not seen as helpful. And I'm curious if you have thoughts about that, because this robot seems almost like the world's best executive assistant, right? They observe you, they figure out what you want, and they do it before you want it. Versus like a spouse who's trying to help you maybe be the best version of yourself.
Yeah, so our data currently is from a single person household, but the thing is this, the original variant with no activity recognition especially has no clue how many people are involved. All it's like, in this household, this is normal. Somebody eats cereal in the morning. Somebody, goes to tennis in the afternoon or does yoga. And so that level of ignorance can be helpful. It actually hurts interaction because it can't be intelligent about asking the right person if they want something, right? And so building on that, I think it's an extra challenge, and we just need much better tracking. This is hard. I mean, this is really hard to do in a real natural household where things move and you're like, I don't know who. Humans are good at inferring that it was, somebody else or the husband's keys or whatever. But yeah, we're not quite there yet. It's a great question and a great challenge.
I have another question in the back.
Yeah, I think
Okay, great.
Hi, my name is Dan. I have another question related to practice. So in some cases, it's like providing practice. For example, trying to keep a habit. I'm wondering how to, yeah, are you going to filter out the practice?
That's a great question, right? There are habits we have we don't want. And what if like I throw my laundry on the floor and the robot's like, cool, I should, right? And so all kinds of reasons why you may or may not want. As was stated in the intro, we actually have a branch of work on towards older adults with cognitive decline. And, use it or lose it is a principle there, right? You don't want the robot to take over certain tasks because you want people to stay cognitively active. And so we are working exactly on that right now, is how do you personalize in a really lightweight and intelligent way what the robot should and shouldn't do in terms of being proactive, because clearly just copying and maintaining the status quo is not necessarily always good, either because you have habits you want to change or because you want to be better than your current self or whatever it is, right? So absolutely.
Okay, I actually have a, okay. The question was, what are the data requirements here? How many examples do we need from the person?
Yeah, that's a really great question that showed all these days of simulation. And so it seems like, oh my God, this needs, I was really surprised that the model more or less converges after 5 days of data. Now that's like 5 really good observation days. I think in the wild, it would take a little bit longer because you're only seeing certain rooms at certain times. It really depends on how often the environment changes. But the simulation, and I didn't show that graph, but I think it sort of gives the impression that it takes 60 days of data for it to be useful. That's just how much we simulated. It actually learns really quickly for most of the types of simulations that we've done. And I think, again, the frequency of the object movements and the frequency of action sort of will influence that. But I think the scene graphs really help simplify the complexity of the world, right? We've really broken, what we've done is like try to take the minimalistic approach again, which is the world is really complicated. There's all this stuff. There's activities, there's preferences, there's individuals, all this stuff. What is the minimum we can actually lean on? And object tracking seems to be it. And it's simplified the world to such a degree that I think it's not as much data as it would seem.
Okay, thank you very much. That's all the time we have. Thank you, Sonia.
So after the keynote, we have our first group of presentations. So our first round. So this particular round is focused more on design-oriented papers that we had during our workshop. So we'll first start with designing long-term interaction for robot-assisted recovery after critical injury. We have Carl here who's going to take it over.
I hope everyone can hear me okay. So I'm Carl. I'm from Edinburgh Centre for Robotics. So I work across both Edinburgh University and Heriot-Watt University. Thank you very much. So a well-structured progressive exercise program is crucial to people who are suffering from critical injury, things like stroke. And social robots have been used a lot to understand how they can deliver certain aspects of this program. But recently in works over the past decades, there's been a large focus on providing verbal motivation. Yeah, so recent works have focused a lot on providing verbal motivation inside singular sessions, although there has been some work over the longer term as well. But we're interested in how can a robot potentially autonomously guide and make decisions over the long term within physical rehabilitation. So of course, personalization is key to doing this. We need to somehow learn over the long term how to deploy certain decisions. And there's 2 key things we need to do this. We need some kind of model of the world over the long term, and we need to learn efficiently from minimal data, right? We can't get a lot of data from interacting with patients. So on our design journey, we looked into two key parts. The first was what happens within a single session, right? This sort of relationship between the patient and the therapist and the behaviors that they undertake during that session. And then over the longer term, what does that structure look like? Looking at healthcare materials, it sort of breaks down between 0 to 3, 3 to 6, and 6+ weeks. So different stages of recovery, right? More intensive exercises, for example. So we needed to understand this. And to do this, firstly, we held a workshop with 7 expert physios from the Scottish National Healthcare Service. So they had an average of around 14 years experience between them. And the aim, again, was to understand these individual behaviors. And we already had created a data set for this, where we performed systematic observations between therapists and patients. And we recorded the sort of episode trajectories of behavior and visualized these models. You can see one on the left-hand side. And we got these physios back to the table and had them sort of annotate and critique the graphs to sort of give us information around more refined behaviors that we needed. So some results for this was that monitoring physical and emotional state is important. We need to avoid repetition, not in the exercises, of course, but in the sort of social engagement. People get bored if it's saying the same thing over and over again. And progress feedback is also key as well. And for the long-term structure, we then held 4 more workshops with 6 physiotherapists to understand the progression here. And this might seem obvious. There's a lot of healthcare resources online as to how patients progress through rehab, but nothing that's kind of in the format that we can translate nicely into some simplified model for our robot. So this phase was crucial. And now we come to the part where we need to understand how we can personalize this, right? So on the right-hand side, you can see this sort of model of a session that contains every possible exercise within it. So this can go from these early weeks right up until the later weeks. And for this, we propose reinforcement learning. So we have an agent seeking to determine some behavioral policy of state to action mappings to maximize some cumulative reward over time. So you can see how this fits well to our problem, right? We have this situation where we want to maximize exercise performance, but also social engagement through the robot's behavioral actions. And we found that our task breaks down into this sort of natural hierarchy, right? We have a session that's made up of multiple different components or stages. So range of motion drills, strengthening drills. And inside of that, those are made up of various different exercise types. And you can break this down further into sets and repetitions, and then finally into this sort of bottom level where it's the social actions that guide those parts of the session. So we found that hierarchical reinforcement learning might work well here, where you have policies at various levels and they control the subtasks that are executed beneath them. So for example, we've got levels 1 and 2 here. So at the top level, we'd have a controller that chooses the exercise types. So we have this patient profile at the top that has these static states. So if you are a patient that has a low ability, you might be performing exercises that you need more assistance in. And likewise, in the higher abilities, you'd have less assistance. And again, at the lower level, we'll control how many repetitions and sets are inside of these. So why do we use hierarchical RL? Well, it reduces the need to learn from a large flat state space, right? And also certain parts of these exercise sessions are repeatable, right? There's parts of the exercises that are similar to other parts of the session. So we can learn within them and then duplicate them and use them for other parts of the session. So the whole idea here is we're creating more efficient learning. And of course, we're here today to talk about long-term learning. So how can we facilitate that? Well, we'll learn inside each of these states, right? We have low, medium, and high. We can perform learning and learn policies inside of these. And when the patient progresses into the next phase of the rehabilitation, they can enter these different states. And hopefully that'll facilitate this longer term learning scope. So the next steps in this project is to, first of all, build an actual perception component. So we need to understand how well they're doing the exercises, right? This is actually quite difficult, especially with upper limb. So we're looking into using IMU sensors to build a classification model to actually tell the robot how well they're performing in real time. We also want feedback on this interaction after we've developed the first prototype, and then hopefully find a way to simulate long-term learning from role-playing data. Get these physios back to actually role-play different stages of recovery and potentially use this to simulate long-term learning before we deploy this in the real world in situ with end users. So that's everything from me. Hope you found that interesting. Happy to take any questions. Thanks. Yeah, it's a good question. Yeah. So the question was around the perception component and how accurate that could be in sensing the exercise data and if it affects the way they actually do the exercises. So yeah, it's a good question. And we found that it doesn't have to be too accurate. In rehabilitation and in the world, the physio just really wants to get the person moving and doing more movement and more exercises. So from that perspective, we're not looking to get exact measurements, but saying that, we do want to be accurate and actually recording how many reps they do, because that's important, right? We need to actually relate it to how well he done last time to get the reward function to work. So that needs to be somewhat accurate. In terms of, does it affect the way they do the exercises? I think we'll find that out in the first sort of pilot sessions. There are small sensors that we're building. We've kind of mocked these up in the lab, but we're looking to buy even smaller ones so we can reduce that effect. Yeah. Thank you so much.
Right. Let's move on to the next talk, if I can find where it is. Right. So we now have Ellie, who's going to talk about something's not with us today, right? Oh, it's going to talk about Prosody for intuitive robotic interface design. It's not what you say, it's how you say it. Yeah. I'm sorry, probably we just need to do that. It's fun now. What?
Hi everyone, my name is Sanoubari, and this is about, all right, thank you. This is about a work that I did in Google DeepMind Robotics. At the time that we started doing this work, it was just called Designing Intuitive Robotic Interfaces. Prosody was not a word that I was familiar with at that time. So on the off chance that you're on the same boat, prosody is the music of speech. As in, once you take the words away from speech, whatever that remains is what we call prosody. So in other words, it's not about what you say, but it's about how you say it. And this paper is about how we can use prosody for intuitive interface design. When we started this project, it was motivated by a famous demo from 1968 retrospectively called Mother of All Demos. And in this demo, this American engineer, Douglas Engelbert, basically presents the first ever GUI. He brought up the idea of like mouse and windows and menus and icons. And this is what has sort of impacted how we're using computers to the date in 2024. And the main question that he asked was, if you had a computer that was backed up by if you had a computer display backed up by a computer that was immediately and instantly responsive to you at all times, what would you get from that? So what we ask here is, what if the computer was a robot that could move around in your space? How might we design an intuitive interface for controlling robots? So we had a research through design methodology. And basically what I mean by that is that the robot was pretending to be intelligent, whereas it was actually being controlled by a wizard. And the human in the room was told to act out as if the robot was understanding whatever that was coming to them naturally, as in we were asking them to act naturally and just say whatever that they feel like the robot should understand. In the meantime, a wizard was pretending to be the ears, eyes, and the brain of the robot and mapping whatever that was going on in the room and all the interactions to very basic robot control directives. And what I mean by the basic control directives is what you see on the right end of the screen, all of these arrows. So I had a command line interface, and I could just like have the robot go right, left, stop, forward, backward, turn right, turn left. And we had an obstacle course, which was basically a 2D navigation task. And the robot would start at the middle of the room. And people had to sort of instruct the robot to go pick up 3 balls, pick up as in go over 3 balls in order of RGB, and go back to the center of the room. We had 10 participants, 1.5 hours of recorded video. And the first thing that I did was trying to transcribe the videos and see if I can just use the transcribe commands to just figure out, okay, what would, which one of the commands, the directives would I actually choose for that? That did not work, failed very quickly. I'll give you examples of why. So I figured maybe it would help if I had more understanding of the visual cues of what was going on in the scene. And that also didn't help, because scenes are complex. And I was thinking about this for a long time, and I was thinking, how come I cannot, like, I'm seeing what is happening, I am looking at the commands, how come I cannot map it to a robot control command? Because I was not that confused in the room while I was wizarding the robot. Turns out the big problem with NLU is people, because people cause all sorts of robot problems. For example, they assume competence by saying, follow me, without really knowing what the robot can or cannot do. They might say, go over it, really assume that it understands the context and has some common sense to know what it is and how to go over it. Or they use sarcasm by saying, where are you going? Instead of saying, come here. They don't necessarily finish their sentences. They say, turn there. And you got to figure out where. They also contradict themselves by saying things like, don't, slow down. Once you're looking at this as a transcribe command, it's don't slow down. Anyways, I'm going to show you one example of like the sort of problems people cause for robots where they're using the same words, but they actually mean totally opposite things. You're not hearing this, right? Okay, I'm just going to do another share and no. Well, we have an audio problem. Okay, let's do it again. Oh, right. Yep. Great. Amazing. Okay, let's try again.
Straight forward to the red wall. Stick to the left. That's great.
Okay, I can actually just like repeat what you say.
Nice.
Basically, in that video that you just didn't hear, the person saying, go to the left, nice, nice, nice. Nice means keep going, keep going. In the other video, the person's like, okay, now turn there, nice. That means stop. Words are the same, completely opposite meaning. And this took a lot of rewatching of the videos to figure out. But essentially, I realized that when you listen to them, even though they're both nice, they're not at the same time. And the difference lies in prosody, which is speech beyond text. And I kind of explained this a little bit, so I won't go into too much detail. But the thing that I want you to take away from the slide is that prosody is not random. We understand it because there are temporal configurations that actually carry meaning. And so what prosody is, what prosodic constructs are, is basically a specific configuration of prosodic elements. And when I say elements, I mean things like the frequency of your speech, the fundamental frequency, the pitch, the duration of silence, the duration of speech, how loud you are, and so on. So prosodic constructs are temporal configuration of these speech that have specific meanings. And they're pretty magical because they're not necessarily closely aligned with words, and they can be present to certain degrees, as in, you know, when I am using a prosodic construct to convey something like urgency, you don't just understand that I'm conveying urgency, but you can tell between two different, you know, utterances which one is more urgent, as in it's a matter of degree, and people have very tight control of it. And it can also be superimposed, as in you can have different prosodic constructs sort of be overlaid on top of one another. We observed specific prosodic constructs in this paper. I won't go into too much detail, but I want to just I have the names here because you can look up these names in the book here by Nigel Words, and you can actually see these, like, what, you know, when I say high priority interpolation construct, what that means in terms of the specific prosodic features and how we can detect it. But basically, people use that for conveying urgency, for example, by saying, go forward, left, 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 means left right now. They used backchanneling for saying, you know, kind of encouraging continuation. And also they had things for, you know, things like good job or bad dog, which is basically reprimand or positive evaluation. So what this means is that once robots have this understanding, they can effectively use it for reinforcement learning. As in, once they understand when you're saying no or when you're encouraging them, they can use that for lifelong learning and some sort of personalization. I will stop here for questions. Sorry that went too long. Yeah, so the question was, how can prosody be used for personalization, especially with, for example, people on the spectrum? They might not be, you know, sort of, they might take things more literally and not, I think there's an assumption that they may not be relying so much on prosody, but I would cast doubt on that assumption, because I think we developed prosodic understanding and prosodic communication way before even like verbal understanding. At 9 months old, if a child does not understand your prosody and is not reacting to your peekaboo, they have serious developmental problems, and they should, like, you know, you should actually have someone look into that. So prosody is very innate and is very, very pervasive. And how it can be used for personalization? Well, there are things you can have you can understand a lot about, you know, things like speaker recognition, or have user traits that you're carrying from that. But also, people are actually, there's a lot of individual differences in prosody. So I think that in itself can potentially be used as a marker for how this person specifically communicates, how they are using prosody, and what do they mean by it in specific cases. I don't know if that answers your question. All right, great. Amazing. Very good. Thanks so much.
Sorry, everyone, for running a bit over the schedule with the technical difficulties. We're going to have a coffee break now, so you can just relax and just talk with everyone. And we'll be back here at 10:30. All right, see you.
Thank you, everyone, for being back. Thank you for being patient with all of our, you know, electronical difficulty this morning. Okay, so we'll continue now with our second keynote speaker. I will let Mariacarla introduce Silvia online.
Okay. Hi, everyone. How is going over there? I'm really sorry I couldn't be there with you, but I hope you are enjoying the workshop. As for me, apart from some technical problems, I'm enjoying the workshop as if I were there with you. So actually, technical problems make everything more realistic. So, you know, it's really like I'm there with you. Okay, so let's move on to the next invited speaker, who I'm really very proud and honored to present. And she's Silvia Rossi. She's Associate Professor of Computer Science at the University of Naples, Federico II. And she's the head of the PRISCA laboratory, that is the Laboratory of Intelligent Robotics and Advanced Cognitive System projects. She obtained her master's degrees in physics from the University of Naples, Federico II, and PhD in Information and Communication Technologies from the University of Trento. He's an associate editor of several renowned journals of robotics, such as IEEE, Robotics and Automation Letters, the International Journal of Social Robotics, and the Journal of Intelligent Service Robotics. And she was also the general chair of Roman 2020 and Roman 2022, as well as program chair of ICSR 2020 and 2023, and also co-chair of workshop and tutorial chair of HRI as well in 2019. And she has been involved in her career in several national and international EU projects, and currently she's a principal investigator and coordinator of the European Training Network on Personalized Robotics as a Service-Oriented Applications, the PERSEO project. And her research interests include but not limited to multi-agent systems, human-robot interaction, cognitive architectures, and behavior-based robotics. She published more than 150 articles in international journals and books. But apart for her biography, I would just spend a few words for Silvia, because I've known Silvia for many years, and I've been really honored to work with her, because apart from technical skills, I really appreciated her soft skills. She's like a force of nature dedicated to her work and her research, and capable of coordinating multiple peoples and projects at the same time, so with an incredible multitasking ability. So all my respect goes to the tireless Silvia, who is giving the talk titled Proactive Behavior and Theory of Mind for Behavior Change. Silvia, the floor is yours.
Thanks a lot, Mariacarla. Can you hear me well?
Yes, we can.
So first of all, thanks a lot for the very nice and kind of introduction. Now you raise a lot of expectation. Let's hope that we'll be not disappointed. And first of all, I have to say that I'm really sad that I cannot be there in these days. But we have in Italy a European Robotic Forum in this same week. So it was kind of tough to be in two places at the same time. But I hope you will enjoy the conference and the rest of the workshop too. So first of all, as Mariacarla said, I'm from the University of Napoli, Federico II. And we are kind of proud that this year actually we celebrate 800 of from the foundation of the university. So Federico II, actually, it's the oldest public university. There are a lot of private universities in Italy, especially also that are older, but they were private. They were under the church. So our was the first public one to be instituted in 1224. So that's why I want to acknowledge that for you too. So I'm head of the PRISCA lab. So in our lab, we mainly focus on different topics that are all linked, of course, to have and develop agents' autonomous behavior. So from one side, we work on how to make a robot aware of its surrounding space. And this is for, of course, for developing machine learning for artificial perception, but we are a lot interested in how this perception can be used to build model of the user. And then, of course, these models can be then used for making the robot behavior more adaptable. And in particular, in this very last few years, we are a lot interested also how to make this adaptation more in a proactive sense, because many times when we talk about adaptation, we are still dealing with devices that just react to external input. So we want to understand how to make this system much more proactive and so better adaptive with respect to the user. And then, of course, when we have a system that changes its behavior on time, we have also problem of trustworthiness, because, of course, people that are not able to predict and recognize easily the behavior of the robot may be not willing to use the robot in principle, or may feel some discomfort in using the robot. So we are start working also on how to measure the legibility of the robot behavior, and also the predictability, and also how to, for example, make a robot able to explain itself once it's changing its behavior. So we do this kind of research, as Mariacarla said, in the context of different projects. For example, the one that's more related to the topic I'm talking about today, it's the Perseo project, which deals with the network, European training network for personalized robotic as service-oriented application. But we have a different one funded by European funding, but also we have a project funded by the national Italian ministry, because in this period in Italy, we have a lot of funds that are called recovery funds that are used for speed up a little bit research after the pandemic, the COVID period, and to increase the research in Italian area in general. So in this topic, I want to speak a little bit about one of these national projects, which is called BEACH, that stands for Personal Robot for Behavioral Change. And so it's a project that we have in joint collaboration with the CNR from Rome, but also from University of Genova here in Italy. So the idea is try to have a personal robot, so personalization in robot behavior, in order to have a change, or attempt to have a change in the behavior of single users. So all the factors that we saw at the beginning of user modeling, personalization, adaptation, legibility kind of apply also for this project. And of course, we all know that actually the embodiment of the robot, it's extremely important. We talk a lot, okay, let's make difference between having the same application of mobile phone on tablets or a robot. We all know that there are a lot of substantial differences due to the fact that we have an embodiment, so a physical robot, but also we believe that it's not just that, but it's more on the complexity of the interaction that we can have with a robot that actually can make some changes and have some effects on the user. So we have been working on personalization from a long time, and typically when dealing with personalization, the first thing you can come into your mind is what kind of assistant a robot can adapt. So how to decide which type of assistance is the one that's best needed by the user. But actually, we want something more, because we want to focus on also how this assistance is provided. So first of all, we have to understand when the user acquires such a distance. Also in the first keynote, we see that the intrusiveness of a robot, it's a kind of important. So understanding when it's time to interact, when it's time to assist, is something that could make the difference between a robot that is used for a long time or not. But also how this intervention have to be provided. So in terms, for example, on how confident, how autonomous the robot should be while providing this intervention. So maybe you are kind of young, but when I was young, there was this funny things called Clippy on Windows that can pop up every seconds, and typically everyone would just closing it and shutting it up because it was too intruding, it's too annoying. So we don't want the robot to act like Clippy. We want robot to be able to understand how exactly it's the time to intervene and how they should provide such interventions. So we thought, okay, first of all, let's try to understand how we can get a lot of data on user behavior. Of course, with data that is not in real human-robot interaction in a physical environment. So we want to understand if we are able to collect data in a different way. So we thought, okay, let's try to make our approach as a sequential one. So we have a framework where we start learning from simple interactions, from simple things, maybe learning online, having, for example, user to interact with the system online, and then eventually come to the real human-robot interaction. So we started from this example where we have like a cognitive task to be performed, and we let a lot of people playing online with the system in order to learn their behavior. But of course, one important thing when you try to learn data that you have to use with the human-robot interaction from simulation or from learning online activities, then you have to be sure that your data can be usable also dealing with the robot. So even in the first stage of the learning process, we kindly want to have the user the possibility to ask for help, to request help to something that is a virtual avatar in that case, but can be mapped in a robot eventually in a second stage. So we define this framework that from step to step, like add additional capabilities to the system in order eventually to have the last round when the user will be able to interact with the robot. So we had this very simple assistive task, which is a memory task where you have to remember like a sequence of cards, and you can see that cards are quite similar with each other. So it's a very difficult task to remember even for me. So the system will show the cards, and then we'll ask the user to repeat the sequence. And then of course you can ask for advices, and each advice will like take you off some scores. So if you ask for very complex advice, then you get less scores than if you ask for simple advices. And then we thought, okay, first of all, we cannot start from scratch. So we cannot start learning a behavior, assistive behavior, without having any information about the user. So we started to say, okay, let's understand in this domain which kind of user model we can use as a prior for our system. So we thought that since it's a game, we can use, for example, a user model based on game behavior. And so we have, in this case, 4 types of game behavior that are called conqueror, participant, manager, wanderer, that actually model how a user is addressing its want to compete or want just to win or want to get the higher score when playing a game. And actually a user could be also all the 4. So it's not have to be one of the single model. It could be something that it's a mixture of different models. And then so we collect all this data, and we actually discovered that it was true. I'm sorry, the labels are Italians because they are from a master thesis of one of my students, but we actually discovered that different type of assistants were asked with respect to different type of users. So users were more inclined to ask some kind of advice or some kind of help with respect to their initial background, initial user model in gaming. And then so we start to say, okay, we have all this data, and we try to understand how to model something that could be useful then for our robot in order to learn how and when and what type of assistance it has to provide. So at the beginning, we end up with a very complex influence diagram where there were a lot of variables to be taken into account, but it was too complex. So it was something that was not actually giving us any insight of the final result we wanted. So at the end, we thought, okay, what if we are able to isolate the three type of assistance we want to provide. So we want to understand what type of assistant, at what time, and with which level of autonomy or confidence we want to provide the assistance. And so we come up with the 3 very simple utility diagram that actually give us the insight and give us the way to reason on what is happening in the system and when and how and what type of advice the robot here, the simulated robot here should provide to the user. And so we learn with a couple of steps this influence diagram, and we tested, for example, in real interaction with the Fura robot. That's an example of the interaction.
Buona partita.
Of course, it's in Italian because we have user in Italian, but it just from time to time is asking the
Ho
user.
scelto di utilizzare per te l'aiuto nascondi carta. L'hai gradito? Penso che ti possa servire un aiuto.
And you would hear that is kindly giving advice in a different way, either giving them directly on the website or asking if they
Ti
want
suggerisco di
advice,
utilizzare l'aiuto indica posizione.
or just giving some suggestion in a very general
L'hai
way.
gradito?
So the level of autonomy and confidence the robot use actually change during the interaction according to the user behavior. So what was our results? Actually, were quite surprising because respect to the level, the number of trials and the level that the people achieved that were not significant between the two groups. So we compared our proactive robot with a random one, which is typically the tougher one to try, because typically when you have a random system, it's enjoyable because it's kind of try everything. So at the end, it will match what we are doing. But surprisingly, we had that people interacting with the proactive robot got a higher score and did fewer mistakes, and actually receiving the equal number of assistants. So the number of times the robot was intervening was the same, but the people were getting higher score with the less mistakes. And also the number of assistants activated by the user were much more less. So people actually did not feel the need to ask for advice to the robot because they felt in control and they felt were assisted by the robot. So these results were encouraging, but it's not enough. It's not enough because actually we know that when dealing with robot, there is some problem linked also to the compliance. So I want to show you these two videos.
Sono Pepper, piacere di conoscerla. Tra poco faremo alcuni esercizi insieme.
It's giving some exercise that are used for screening about the Alzheimer's disease. So it's called MOCA. So it's asking a user to make some exercise. For example, in this case, it's making
Da uno di questi fogli di carta in un pennarello e copi questo disegno il meglio possibile. Poi aspetti che le dica cosa fare. Può iniziare.
Here you're asking for making a drawings of a cube.
Andare avanti con la seconda parte della nostra attività. Mi dice il nome di questo animale?
Leone.
So it's asking
Mi
for
dice il
names
nome di
of
questo
animals.
animale?
Rinoceronte.
Mi dice il nome di questo animale?
Dromedario.
Per favore, ripeta le parole una per una. Faccia. Velluto. Chiesa.
At the end, it's asking to memorize some words and repeat them at the end. So, what happened here?
Leggerò lo stesso elenco per la seconda volta. Provi a ricordarle e a ripetermi tutte quelle che riesci a ricordare.
The same interaction,
incluse le parole
so
che ricorda
repeating
dalla
the
prima
sequence,
prova.
but this time,
Faccia. Velluto. Chiesa. Margherita. Rosso.
Faccia. Velluto. Margherita. Chiesa. Rosso.
so this time, since the user had paper and pencil available, he took advantage and wrote down the words that he had to remember. So this means that when we are using robotics and adaptive robot to provide assessment and training, we have to somehow to be sure that they will be stick by the rules and not cheating. So in our idea, the this non-compliance could also be caused by the level of complexity of the interaction that's provided, the level, for example, of interaction, the level of behavioral style. In that case, for example, we thought, okay, let's try to have different personalities in the robot itself, and let's see if this would affect the compliance and the stick by the rules during some cognitive test. And indeed, it was the case, because actually some of the task, or some of the users, the majority of the users were more compliant in case of, for example, an authoritarian personality or a friendly personality. So I think I have a couple of minutes left, right? So in this couple of minutes, I want to just show you what we are doing now, because out of this experiment, we found out that somehow also the fact that the robot was acting with different personality had an impact on how people were attributing theory of mind capabilities to a robot. And we think that this kind of thing is important because the attribution of mental capability to a robot could be also important when you have to be compliant. So you have to follow the rules, and also you have to deal with the possibility of a robot making errors. Because of course, a robot will make errors because it's a machine, so it won't be perfect. And we thought that simulating this kind of capabilities into a robot may help in alleviating the loss of trust, for example, in case of error and stuff like that. So we are in the last few years developing few examples that we are doing actually in the context of the error project, where we make the robot fail intentionally, and we understand if the fact that the robot may show some theory of mind capabilities may alleviate such failures and may so have impact more on how people trust and how people will follow the suggestion of the robot. So I'm not going in detail to this because I think we are almost over, and I think I'll conclude here. Thanks a lot.
Thank you very much, Silvia. I don't know, perhaps you guys can help me in asking if there are some questions from the attendees, or also from the chat.
If you have any questions, I can pass it on the mic. Mariacarla, maybe you can start.
There are no questions? Are no questions from the attendees?
Mariacarla, can you start with the questions and then we'll follow up?
Question when there's
Okay, so
things.
I can,
Yeah.
Okay, so I have a question. I know there is not enough time to talk also of theory of mind, but I was really interested in knowing how personalization, in your opinion, is related to theory of mind, the achievement of theory of mind between humans and robots, if it is necessary, or yeah. So what is the relationship between the two?
Yeah, indeed, it's. I think that two aspects of the same thing, because of course, showing ability of theory of minds means that you can show that you are able to understand intention and goals and reason on that, on the other partners. So that means that you are able to personalize, because in order to personalize, you need the user model, you need to understand what is going on, what are the intention, what are the goals of the person. So are two faces of the same thing, I will say. So you have to do it, but we also have to show it, because you have to show that you have these capabilities, because then if you just adapt without making the user knowing how and why you are adapting, that could be also counterproductive.
If there are no other questions, I do have a correlated questions to a related question. And it's about how you think that, in what extent the long-term learning and HRI can support the creation of theory of mind?
Well, I have to say that actually long-term learning is the challenge, because what we have up to now, it's learning models, but models can change over time. So the challenge the next future will be to understand how this small model can be made dynamical and can be used and can be relearned or through, for example, transfer learning. So try to understand how this could be something that is not, once it's learned, is not fixed and could be evolving and adapting in time.
Okay, so thank you very much, Silvia. I think we can, I can pass the floor to Andreea. Andreea, are you going to introduce next? So let's thank the speaker again. I'm not able to hear from your applause, but let's thank the speaker again. And I leave you the floor, Andreea.
Thank you. Okay, so next up we have contributed talks. Okay, so first up we have federated learning of socially appropriate agent behaviors in simulated home environments. And this one is an online talk. So we have the speaker here in Zoom. Great. I will make you co-host so that you can share your slides and take it away. Okay, Saksham, can you try sharing your slides?
I guess it is visible.
Excellent. Okay,
yeah.
The floor is yours.
Yeah, thank you. So, hello everyone. My name is Saksham Sekhar, and I'll be presenting our paper on federated learning of socially appropriate agent behaviors in simulated home environments. So, let's get started. So basically, there has been an increased integration of social robots into daily life that needs to ensure that the behavior is incompatible with social norms. So to achieve the widespread application, federated learning comes into play, and it enables the robots to learn from unique environments while benefiting from the shared information from the other robots as well. And in order to learn different types of tasks and overcoming the issue of forgettability, continual learning is to be integrated on the client level. So in this paper, we present firstly the benchmark of federated and then federated continual learning for such application of social robots. So the benchmark basically focuses that each client learns to predict the social appropriateness of various robot actions. So the challenge is basically addressed by two main benchmarks. So our paper first introduces federated learning benchmark to assess the strategies for individual robot learning while leveraging collective experiences. Then the problem also extends to federated continual learning benchmark, adapting federated learning based methods with state-of-the-art continual learning techniques. So a critical problem is effectively training the robots to adapt and continually learn socially appropriate behaviors in different contextual settings. So as we were exploring simulated environments, so we used a simulated living room scenario. And for this, we used the ManusDB dataset. And the dataset basically contains 3D scenes created with Unity of Pepper Robot, co-inhabiting a living room space with other humans, adults, and children, as well as animals under different social settings. So basically, there are two different types of like tasks for the robot. That could be either within a circle of influence or direction of operation. And like 8 different tasks are set up for the robot, as you can see in the figure as well. So in our benchmark, we are using 29-dimensional scene descriptions from the for predicting the social appropriate. So moving on to, we all know that basically centralized learning is when the robot shares the data directly to the server, and server learns a shared model, which is then used by the robots individually. So in order to move on, we have a federated learning setup in which all the robots are learning locally, and they are sharing their weights or gradients to the server to be aggregated without sharing the data, and it also focuses on privacy there. Now, we have basically used 5 different federated learning strategies: the Fed average, Fed BN, Fed prox, then we have Fed opt-adam, as well as Fed distance. So, moving on to the results of federated learning benchmark, we had 2 different scenarios, one with 2 clients and the second with 2 clients. So, first we will be talking about without augmentation, that is, we are using the 29 descriptor as it is, and we can see that Fed prox in the case of 2 clients had the best performing in terms of Pearson correlation value, while Fed average had a lower loss, but it was comparable with Fed prox only. And in without augmentation only, we see in 10 clients, we had Fed prox again with a good Pearson correlation value, while Fed opt-adam had a similar, not so different loss, but yeah, Fed prox being then the second best. Now, if we tried the experimentation with augmentation, Fed average had a lower loss as well as a better Pearson correlation for both 2 clients as well as 10 clients. Now, moving on to federated continual learning. So we have a similar federated learning framework setup, and each client has its own continuous setup as well to learn multiple tasks with time. So for federated continual learning, as we saw in the federated learning results, we had Fed average to be a better performing strategy for our multi-level regression setup. So we used concatenated federated learning of Fed average strategy along with EWC, EWC online, then SI and MAS. So these 4 were our using the basic strategy, and then we had naive replay as well. Okay, so moving on to the federated continual learning results. So basically, we had again 2 clients and 10 client setup. And task-wise, if we see that, as I mentioned earlier in the dataset, we had circle as well as arrow. So task 1 was set up as circle, and task 2 had the arrow set. And in terms of the test set, after task 1, we used only the circle part, and after task 2, we checked our performance on both circle as well as arrow to see how much the robots still have the knowledge of the previous task. So in 2 clients without augmentation, we were able to see that Fed average EWC online was performing good for task 1, but at the end, when both tasks were tested, we had Fed average NR to be having lower loss, while Fed average MES was a close call with a better PCC value. And similarly, in 10 clients, Fed average EWC online again had, for task 1, it was a better performing, but at the end of task 2, NR had a better PCC value, while loss was comparable with Fed average SI. So basically, Fed average NR turned out to be a good performing method, given that it stored some fraction of the data from the previous task in its memory buffer. So when we augmented our data set, we saw that after task 2 for 2 clients, we had Fed average NR performing well in terms of both loss as well as Pearson correlation value. And for 10 clients, we had the loss was better for Fed average NR, while Fed average EWC online had a comparable PCC value with Fed average NR still being the best. So a takeaway from our presentation would be we introduce a novel benchmark for learning social appropriate robot behaviors in human settings, and Fed average being a simple and a robust federated learning method, and it aligned well with our traditional ML baseline scores. Then adaptation, while adapting federated continual learning, that is, we integrated federated learning with the state-of-the-art continual learning strategies. And then we, in future, we are focusing to use the direct scene renders that are available in the ManageDB dataset, and using those for more resource-efficient continual learning techniques. So yeah, that's it.
Thank you. We have time for one question from the audience.
But I can take the question in person as well, just to quicken things up, if that's helps.
And we have 2 microphones this time.
Yes.
Okay.
So here you show the results of federated learning on different tasks, right? And the performance is decreasing. I would expect that as you include more tasks, the performance might drop to actually 0. Is that the case that you see in the experiments? And if so, how can you go around this issue in the federated learning context?
Right. So exactly, that's the problem of forgetting that we go through. So if you look at Fed average as it is, you'll see this effect of a new task completely overwriting previous task knowledge. So you'll get the scores that you see over there is actually an average over the 2 tasks. So that's why you see an average shift. But if you look at the individual scores without any forgetting prevention mechanism, you'll see the task 1 completely forgotten and completely overwritten by task 2. So that's why we need to augment Fed average of federated learning methods with continual learning objectives. And that's why we use the many different ones like EWC or any kind. These are all weight regularizations that try to discourage any changes in weights which are more corresponding to previously seen tasks. And here, in this sort of setup, having a memory buffer with naive replay where you can actually store samples turns out to the best approach, but it may not be the most appropriate approach given the end client resource constraints that you might deal with. So there's a need to sort of look deeper into more so to say, more sophisticated methods to actually do rehearsal or do pseudo rehearsal in that sense, which we cover in the future work that we're trying to look at. I hope I answered the question. Yeah.
Okay, thank you very much.
Cheers.
And now we're going to move on to the next talk. So from now on, our speakers are in person. So please come here to the podium. So next talk is Train Your Robot in AR, investigating user experience with a continuously learning robot. And yes, that's okay. Great. So yeah, let me do this. And yeah, yep. Okay, this looks good. And
great. Thank you very much. Good day, everyone. My name is Anna Bellardinelli. I'm with the Honda Research Institute in Europe. And today I'd like to present you some of the efforts we made with my colleagues here to investigate how users can teach and interact with a continuously learning robot in augmented reality. Yeah. As we heard today from Sonia Chernova and also Cynthia Brazial recently said that indeed robots have been everywhere, but actually the last frontiers for them seems to be our living rooms. And if you want to go toward that vision, I would say that we have 3 fundamental requirements on the human side, beside all the challenges on the technical side. One being, of course, personalization, because people want to interact with a robot that somehow knows them or remembers them. Teachability, so robots cannot come with all possible skills pre-trained in advance. And an intuitive interaction and explainability. They don't want to go through long manuals or training just to interact with the robot. And we have developed a system that is potentially 24/7 ready, at least in a limited constraint scene, can continuously and incrementally learn and generalize and straightforwardly apply new knowledge provided by the user. But this means that we have 2 systems that continuously develop and interrelatedly develop. So on the one hand, through repeated interaction, you have the robot that learns more and more, and you have the user that basically continuously refines its model of what the robot can do. So on the system side, there might be a lot of questions that we want to answer. So how well the robot performs. On the user side, of course, we're interested in knowing how the user can trust over time the robot or can be kept continuously engaged. But what we think are the more interesting questions is also how we can quantify how this interaction affect both the teaching or action strategy of the user and how the teacher's behavior affects the learning. So we had an unsupervised experiment conducted in augmented reality. So we placed the HoloLens in a common space at our office, and we had students and associates working there. We invited them. We gave a video with instructions, and they basically could repeatedly interact with the HoloLens as long as it was free from other participants. And a typical interaction would go like this. So they would put on the HoloLens, start a system, log in with their pseudo ID. Then they would land in a kind of playground state where they would look at the scene, at this kitchen scene, where they could teach simple kitchen tasks. So they first could go in playground mode and try, because of course, in augmented reality, the object manipulation isn't the same as in real environment. And then they would decide to start a teaching episode and answer questions about that, or a planning, so having the robot do something. And in the end, they would log out and answer questionnaire in laptop nearby. So this is how the learning would go. A new skill is basically taught by pressing the Start Learning button. And the robot learns semantically, so observe which effects the teacher actions have. And here we assume that the robot can learn about devices which make object attributes like temperature, aroma, or crispness change. So the robot is always telling the user what it understands. And also there are these AR labels that explain it. So when the user concludes the teaching episode, the robot will summarize what it has learned.
I have learned that toaster changes crispness of bread from soft to crispy, and temperature of bread from warm to hot. May I ask a question?
Of course, you don't want to do the same for every, I don't know, for every item.
Can toaster be used to change crispness of egg from soft to crispy, and temperature of egg from warm to hot?
So the robot generalizes. Now, usually it starts with the items that in the WordNet hierarchy are closer to the one demonstrated. Now this model has already been training on some other stuff. So it asks, for example, for the egg.
Yes. Can toaster be used to change crispness of milk from soft to crispy, and temperature of milk from warm to hot?
No.
Okay, I won't do that. May I ask another question?
No.
It's a bit on the social side we can improve. I agree. And in the end, basically, a progress bar would tell the person how much their teaching improved the skill level of the robot, and this was meant as a gamification element to help to keep people engaged and give them a feeling of what the robot, how much progressed. And then they could just ask the robot, okay, I teach you that. I taught you that. Let's see how if you can now make
crispy and hot.
The white bread.
Okay, this is my plan.
Hot. And then an avatar of the robot would appear on the other side of the table, and show again a bit in a semantic way. So we ignore collision avoidance or grasping. Even the bread is shown as an avatar, but it basically would list all the steps that the planner would come up. So
I would switch
take
on the
the
toaster.
bread, put it into the toaster, and people then would get a feeling of how good their training was. So we have thus far just look at the questionnaire responses. If we have 33 people that list once interact with the system, and we looked at engagement, understanding, and trust perception. And all after the first interaction, all these measures were above, let's say, the dividing line between don't agree and agree. Unfortunately, just 16 people out of 33 came on another day and tried again the interaction. So if we look at the two first and second interaction, it seems like it goes down, but actually all this difference in the three questionnaires are not significant. So at least we managed to keep people engaged. For the outlook, indeed, we have an integrated system for robot training that shows continual learning, planning, and explainable HRI in AR. Preliminary results show that the robot is positively perceived, but actually this is a very limited insight, because the interesting things that we're going to analyze in the future is how this subjective measure correlate with what the participants really did with the robot. So how much skills they taught, how many questions they answered, how high was the score. And with this, I thank you. And if you have any questions, I'm happy to answer.
So how was skill level measured, and is there any notion of like a human teaching a bad behavior and like reducing skill level?
Yeah, that indeed for this score, this kind of score, we had a predefined ground truth that basically was depending on how much objects you cover, this would increase. And of course, we decided, of course, the egg cannot go in the toaster, but that was also to simulate people not to adversarially teach the robot stupid stuff. Also for the personalization, it's your robot if you teach that stuff. So indeed, if you do teach wrong stuff against the ground truth, the score would go back.
I see. Okay, thank you.
Okay, thank you. Okay, next up we have toward measuring the effect of robot competency on human kinesthetic feedback and long-term task learning. And I have your slides over here. Share screen, and I gotta share sound. Okay, take it away.
All right. Hi everyone. Welcome to this talk. My name is Strongo. I'm a first-year PhD student at Yale with Brian Scazzolati and Tesca Fitzgerald. So this talk is going to be about our ongoing user study, and we hope to bring some interesting questions and discussions to light. There you go. Yeah, so the context of this work is, robot learning from human feedback, in which there are already a lot of work on different modalities of feedback, such as like rewards, demonstrations, corrections, and preferences. So the approach is that these works adopt usually assume some sort of assumption on human feedback. So nominally, these ones, including, for instance, human feedback being Markovian, in that the most recent feedback only evaluates the most recent trial, or that it is time consistent. For instance, if a human prefers apples over oranges, it will always do so regardless how long you interact with the robot. And there are some other less discussed ones, such as being retrospective, meaning that you look back in time rather than doing prediction, or incentive driven. For instance, providing feedback is the same thing as maximizing rewards, or path independent or Bellman optimal, in that the human doesn't really care how the robot gets to a goal state. As long as it gets to that goal state, the cumulative reward should be the same. So obviously, natural human feedback doesn't necessarily satisfy one or more of those constraints. So some studies have shown that, for instance, compared to a robot that has been consistently performing well, a struggling robot or a robot that increases in its performance actually receives more feedback at the very end. Some other ones, including, a teacher's prior rewards influences the scaling of the future rewards. So for instance, if the total reward is bounded, the humans have to be very conservative in providing rewards, because ideally when the robot is closer to the goal, it would receive more rewards. Some other studies have shown that, the robot's performance can affect the human's mental model of both the robot and their own teaching capabilities. And some works also shown that, some people use rewards to evaluate the past, and some use rewards to guide future subsequent actions. So obviously there's a lot of factors that plays into how that influences how humans provide feedback. So one of the most important factor that has been shown in trust-related work, which even for learning-based work is more important, which is competency and performance, because that's how we evaluate our algorithms and our robots. So the research question we want to answer in this work is, how does robots' past and current competency at the task affect when and how people decide to intervene and correct the robot's motion. And we specifically study the feedback modality of correction, and we'll talk about it more in future slides. So we design a long series of pick and place tasks in which the job for the robot is to place the block into the matching color hole. So the participants are welcome to interrupt and correct the robot's motion by providing kinesthetic feedback. So here I have an example. So something very special about correction feedback is that it has trust inherently built into this feedback modality. So you can see that, for instance, in this first trial, that the robot is performing rather well. So there's no reason for the human to intervene, as compared to other modalities of feedback in which the human evaluates for every trial. So the second, another thing for correction feedback is that it is rather physically intuitive compared to other modalities such as rewards, where there's more mental math going on in the brain. And you can see here, the human sees that the robot is making a mistake and it decides to intervene and correct the motion. And afterwards, the robot carries on the task. Yeah, so we divide our participants into 4 competency conditions. So the first one is consistently low with only 25, and by competency or performance, we mean like success rate of the task. So where the robot is only performing at 25% success rate, we also have a consistently high, which means like the robot is just like super good. And we also have increase and also decrease condition in which the robot's performances varies. So by design, these competency conditions are to represent a diverse range of agent performances in a very vanilla RL setting. So you can think of, particularly for increase is what we expect to see, and for decrease, you can think of it as like catastrophic forgetting in RL. So we do expect to see some, so the first hypothesis that we propose is that we do expect to see some kinesthetic differences in different competencies. So for instance, I think, so we propose that, in a constantly high competency, we do expect to see people provide feedback with less effort, velocity, and displacement from nominal trajectories, maybe because they feel less frustrated that the robot hasn't been learning from their feedback. So the second hypothesis is that we believe by having a constantly high competency, the human would intervene less unnecessarily. So for instance, if the robot has been performing well, the human wouldn't unnecessarily intervene, i.e. to predict that the robot might fail. We also expect to see higher reliability measures from like our qualitative surveys. So the last hypothesis has to do with the cost of giving feedback. So existing works doesn't usually assume they usually assume that human feedback is readily available. But it's actually the case that, in order to provide feedback, there's some sort of human's comfort zone or like human's workspace that they really prefer. So like by cost, you can think of it as time, monetary, or effort. What we expect to see is that in lower prior competency, human will step out their workspace more frequently and by a larger magnitude because they feel like the robot needs more correction or feedback. So they're more willing to optimize their cost and providing feedback. And as of this moment, we don't have any results to show, but I'm happy to take any questions. Yeah.
So how do you expect to operationalize the results of the study? Like what sort of algorithms do you think you can use to correct for if there are any biases in how humans provide rewards?
Right. So the first phase of the study is of course data collection, and so that's what we're doing right now. So I think like later on, maybe you can use these data to build models of how different history of competencies, which is where we're studying, affect human feedback or induce biases, and you can feed these models to the robots, some like algorithms, and the robots can use these models to map, say, bias feedback to less biased feedback, and maybe that would improve the learning efficiency as well.
Thank you very much. And we have our last contributor talk. Yeah, it stops because I stopped the PowerPoint. Cool, yeah, that's fine. Okay, great. So our final talk towards learning interpretable features from interventions. Erin, take it.
Hi, let's see. Okay. I'm Erin Headland-Body. I'm a student at Georgia Tech with my advisor, Matthew Gomblay. This work is similar to the last one, so we should definitely talk later. Yeah, okay. So like multiple other talks today, a motivating example is assistive in-home robots. And, you know, ideally we'd want robots to be fully capable out of the box, but that's just intractable because everyone's home environments are different, everyone's preferences are different. And additionally, as you know, we're talking about in this lifelong learning, these preferences are going to change over time. And so what we want to do is give non-expert users the ability to communicate their preferences and personalize robots in an intuitive way, you know, that any end user could do. And so, like the last talk mentioned, one way of communicating preferences to a robot, or especially when they fail, is to intervene and then to demonstrate what the robot should have done instead. Additionally, we think this is a good method because people are bad at telling a priori what their preferences are. They're much better at critiquing and saying, oh wait, I thought I thought this was going to be fine, but I actually don't like that. And so that's kind of what we're looking at here. Additionally, we think that there's semantic information in when people intervene. For example, if you intervene when the robot is about to collide with something, you know, you could learn from that information in the environment, the positions of things. Hey, maybe, you know, I'm about to hit something and I should not do that. And additionally, we could personalize based on when people intervene. So if the robot's about to collide with something and people intervene, some people intervene further away than others, maybe their tolerance for what a safe distance is to stay away from obstacles would be different between people. And so in this work, we haven't finished it yet, but we're proposing a framework that learns features for why a person stops a robot and then learns an improved robot policy. And so we start with the pilot study. We've completed the pilot study and we're in the middle of data collection. And then we're going to use this data to train a model and then evaluate our model. And so we've set up a few different experimental domains. These are all household tasks. For example, loading the dishwasher, putting away bleach or different objects on a shelf, sweeping up broken glass, and cutting cookie dough. And so the reason we picked these domains is because most of them involve preferences of some kind. For example, the dishwasher. Some people are very picky about how the dish goes in the dishwasher, where it goes in the dishwasher. And we also introduced, you know, a sense of risk with the broken glass and the knife task. And so in order to keep our conditions the same across participants, we had Wizard of Oz trajectories where we manipulate success and different types of failures. And so, so for example, there's going to be successful trials, and then we're going to have objective failures. Objective failures, the robot fails to complete the task. For example, in this case, the robot is supposed to cut the cookie dough, but it's cutting the people instead. And then we also have subjective failures, where actually the robot is successful at cutting the cookie dough in the end, but it maybe takes the suboptimal path, or, you know, in this case, points the knife at the participant on its suboptimal path. And so we think that some people will intervene at different times in these subjective failures, and some people might not intervene at all. You know, we've actually been finding that, you know, some people are like, oh no, the robot should not point the knife at me. And other people are like, it went a little out of the way, but it's fine. It finished the thing anyway, which was surprising to me, but that's okay. And so our procedure for our pilot and data collection is that the robot attempts the task, and the robot trajectory is shown in green here. Then the person interrupts the robot because the robot is pointing the knife at them. And so the robot stops and doesn't continue the trajectory. The human then says, hey, the knife is in the wrong orientation. And then the human then shows with the corrective demonstration what the robot should have done instead. And we collect that in the blue trajectory there. And so the way we're training our model is that we're taking the robot trajectory before the time of intervention and running that through a feature prediction network in order to learn features. And we want these features to be human readable or interpretable. And so ideally, we're going to learn features like the knife is too far from the cutting board or too close to the table, or the knife is in the wrong orientation. And once we have these features, we want to then train a policy to incorporate these features along with the information of the correct trajectory, which is the robot's trajectory until interruption, and then the human's demonstration after that. And we're going to learn the features. It's more classification with cross entropy loss, and with the actions, we're going to be using mean squared error loss. So then at evaluation time, similar procedure to start with. However, instead of the person then labeling the feature, the robot would say, hey, I think based on your time of intervention that you want me to change the knife's orientation. And if the person says yes, then the robot will hopefully execute the correct behavior. And we want to compare, so this is our method where the robot infers the correct feature. And in order to compare to baselines, we want to have a baseline where there's no features, and the robot learns via like vanilla behavioral cloning. And then we want to have an adversarial condition. So, you know, between ours and behavioral cloning, there's kind of two things that are changing. Hopefully one is the performance and the other is that there's no interaction. And so we want to show that if the robot predicts the wrong feature, that it's not just that the robot's talking to the person, it's the robot is talking to the person and is predicting the correct feature. And lastly, we want to have another baseline where the person is the one that's giving the robot the feature to see if people prefer the robot to guess or if they would rather just tell the robot themselves. So to summarize, we're proposing a framework, and the goals are that we hope that once we train this model, that it will generalize to new users and be a way that people could interrupt and personalize a robot just from simply stopping it while it's failing. Any questions? Yeah, so I kind of glossed over that a little bit. So what we're planning to do in the data collection is after the person interrupts the robot, then they're going to use this graphic interface that we developed to label features. So a limitation right now is that it is a preset list of features, but we did use our pilot study to collect, like just have them give us features in natural language without prompting them anything, and use that to synthesize a list of features that then we're allowing them to choose from, so that then when the model predicts a feature, that we then have a natural language template explanation for what that feature corresponds to. Mm-hmm. Yeah, so right now we're assuming we kind of have templated language, but in the future, obviously, we'd want to incorporate LLMs or something to be able to generate this, and also maybe, you know, something like your work where we then add in new features. Right now, it's assuming that we know the features a priori, but that would be in the future. Yeah.
All right, thank you, everyone. All the contributed talks were excellent. Fewer technical difficulties this time around, thankfully. So I think the next part of the day is the debate. And we
talked about adaptation, right? And with adaptation, things can go wrong. Unfortunately, and so we have Tony today. So how Tony decided to. Tony decided so before we start the debate, we want to get your opinion on this first. I don't know. It doesn't work. I can speak like that. That's totally fine.
Wait.
So, ooh, that's loud. Okay, so what do you think? I'm gonna give a poll right now on robots should use lifelong learning in all applications, such as like assistive, education, household applications, and warehouses. despite privacy concerns. So we have the Menti poll here. And if you can, it should be working fine. Let's try it. Okay, if you can just like scan the QR code or just go into the website and enter the code and write your responses. I'm just gonna leave it on in the meantime. And Tony and Haywan, you can just grab seats in the here.
Can Zoom hear me from this other microphone?
Yes.
You can't, it doesn't work?
Yes.
Okay, let me just explain it. I think it started over. Maybe? That one? It works now? You can log in? Perfect. Okay. Just join at the code and let's see how it goes. In the meantime, Andrea is going to start the introduction. Perfect.
I also learned how to make this microphone work. Press, make sure this is green. Okay. Great. Okay, so I'll get us started with some introductions. So we have 4 wonderful debaters today. First, we have Tony. So Tony Belpayam is a professor at Ghent University and a visiting professor of cognitive systems and robotics at Plymouth University. He is a member of ID Lab at Ghent and is associated with the Center for Robotics and Neural Systems at Plymouth. His research interests include social systems, cognitive robotics, and artificial intelligence. Yes. So we have 2 in person and 2 virtual debaters. Should I switch the screen? Here we go. Okay, and Georgia. Yeah, we see you, Sid. Hi, Sid. Yep, Georgia, can you, oh, Georgia is over here too. How do we there we go, gallery?
There are just way too many pixels of me. Okay, now that's fixed.
Maybe pin the 2, me and Sid.
I need to pin both of them. Can I do that? Pin and add pin. There we go. And LEAP-HRI, this one. Add pin. Great. Excellent. All right. Great. So our second speaker, Georgia, virtually. So Georgia Chalvatsaki is a full professor of interactive robot perception and learning, PEARL, and the DFG Emmy Noethler research leader of the IROSA group at TU Darmstadt, Germany. She was accepted into the renowned Emmy Noethler program of the German Research Foundation in 2021. Thank you, Georgia, for being here. Then we have Haywan, who is an in-person speaker. Thank you. She is a research scientist at the MIT Media Lab and a visiting academic at Amazon Labs. She co-directs MIT's initiative on responsible AI for social empowerment and education, RAISE, and leads the AI augmented learning teams. Park's research centers around constructing socially embodied AI agents that can aid human growth across a gamut of aspects on motivation, health, emotional well-being, creativity, and resilience. And lastly, our 4th participant, who is also online, Sid, Sid Srinivasa is a professor at the Paul Allen School of Computer Science and Engineering at the University of Washington. He moved to UW in 2017 after 18 years at the Robotics Institute at Carnegie Mellon University. He founded the Personal Robotics Lab in 2005 and is an IEEE Fellow for contributions to robotic manipulation and human-robot interaction. Thank you to all of our debaters. We're so excited to have you here today. Okay.
Okay. Thank you. It still doesn't work.
I think
Now it works. Now it works.
Now it works. Okay.
Yeah,
Working.
yeah.
Okay, cool. I'll just speak loud. It's fine. Thank you all so much for coming. Hemo and Tony, Sid and Georgia, you're fantastic. Thank you so much. I'm really looking forward to this debate. And before we start, let's see what the audience is actually almost 50-50 on this. Wow. This is perfect. This is really good. totally brings up the discussions. Okay. So let's go back to stop sharing. We don't want to go to Zoom? Yeah, stop sharing.
Okay. I want to also start that I'm not like fully against this statement. I do personalization in my work, and I do think personalization is one of the key component of future robot applications in these multiple domains. But the reason I voted for against is that personalization apply to these domains despite privacy concerns. I just didn't agree with that statement because personalization should incorporate privacy concerns in its methods and approaches. So I am against that statement that we shouldn't disregard privacy concerns when we are personalizing. It should be incorporated within the approaches we take.
Hi, thanks. I might be slightly less coherent than usually because I didn't know I was going to be on this panel until a few minutes ago. So, and apparently I'm against lifelong learning at all costs, even at, privacy, right. Okay. And it kind of aligns with what I really think. So we shouldn't give up privacy. But the problem is that privacy is really a very slippery concept. I notice it everywhere. People try to kind of get a grip on privacy and try to kind of tighten up legislation around privacy. In Europe, for example, that's incredibly important now. The European Union is coming up with all kinds of sweeping legislation, the AI Act, the Data Protection Act, and the Digital Services Act, and they try to kind of understand what privacy is. But privacy is evolving, and I think that as a user, if we will kind of users of the future with a robot in our home, that we are going to be happy with giving up some of our privacy to get a better performing robot, but perhaps not just everything. And it's going to be up to us to decide on what it is that we are willing to pay for particular functionality of a robot. We are going to pay with some of our privacy, and that's fine. So it's not black or white. It's not what kind of. I'm going to say I'll sit in the middle between for or against. Yeah, is it allowed? Yeah. Okay.
Play the devil's advocate and go for both sides. And on the other side, can we start with Sid? Why are you for this statement?
Sure. Thank you so much. Everybody can hear me now? Yes, great. First of all, it's a pleasure to virtually be with you all. It's a little embarrassing. I'm not that far away from you, but I am certainly in gloomy Seattle, wishing I was in hopefully a warmer or at least a sunnier place. So I think I do agree that this is a very important debate to have. I think we all agree that robotics has the potential to transform society. I've been building robots for half my life, and I certainly don't drink the robotics Kool-Aid. But I think we are working on robotics because we believe that the societal good that can come out of it is material and significant. I work on assistive care, and I can see the direct impact of the work that incredible amount of researchers are doing in enabling and empowering people who are in need of care. So I think we agree, I think, among all the debaters that robotics is relevant. I think there's a second question around lifelong learning, which is slightly thornier since it does open up a lot of privacy issues. I think we also agree that lifelong learning is a critical component for robots to work in the real world. Whether it is personalization, like was just mentioned, about how a robot can work for me, not just something that comes out of the box and doesn't adapt. And also about open worlds, which is the theme of the LEAP-HRI workshop, of how we're actually able to deal with worlds that are not previously completely defined and address previously unseen data distributions that we might encounter. I think from my point of view, privacy is also incredibly valuable and important. None of us, particularly in this time and age where there are cameras everywhere and there are leakages of privacy that happen at all times and that continue to happen. But for me, the ability for us to address those concerns comes directly from understanding the technology and in being able to regulate it, rather than avoiding the technology completely. And I think none of us disagree on that. And also, I think history has shown us that legislation almost always trails adoption significantly. And so I think rather than staying away from this altogether, I think of my duty and our duty as scientists who are in this field to actually participate wholeheartedly in the legislation of robotics and in the legislation of lifelong learning, such that we can together make lifelong learning for robotics work while still embracing privacy.
Great, thank you so much, Sid. And Georgia?
Yeah, so I think I agree with what has been said before. So I think we have two people that come basically from Europe. So for us, the situation can be seen quite different from the one of people from the US or other areas in the world where they have not been under this umbrella of the AI Act that basically now imposes specific regulations about what we are going to study, how we are going to study it, where we can take our robots or not. So there is also a practical aspect there. But yeah, in general, like maybe to just recap what we have heard, yeah, lifelong learning is important. Lifelong learning is the only way that we can have this kind of transformative revolution of robots being able to assist us in all these areas and domains that you have mentioned also on your topic, like education, household, in care, in warehouses. So of course, personalization is very important. We should not also forget the fact that much of the data, for example, the skill set that we are going to equip our robots, if we are, for example, a big company that we are building some robot with some behaviors, may come mainly from the web world. So the question is, how do these robots adapt also and are inclusive of people that come from other societies, but still are in need of those robots? They still need care robots. They still need warehouse assistive robots. So we can imagine all these things. Even in education, we can imagine our lifelong learning robots to be able to adapt to the teaching requirements or methods, to the unique, for example, requirements of every person. So this will make robots even more inclusive and adaptable to many more environments. And of course, we have the concerns about privacy. And we need to somehow safeguard the sensitive information. But this doesn't mean that we should necessarily prevent us from getting information. So the question is, how do we build this algorithms for lifelong robot learning for human-robot interaction, considering how to safeguard this information that we may collect. Of course, this is a question of who collects the data and who builds the algorithms, but this is, I think, a very big discussion to do maybe later on. So yeah, overall, I agree with the people that the other debaters, that they all said that we need to somehow develop some ethical, for example, guidelines, some privacy preserving safeguards, some regulatory frameworks. The problem is that we should not also impede progress. And we should not impede, we know that we need the data, we need to put robots, this is what we see now in research, right? Everybody tries to put the robot out there to collect information, to collect data. And if you are not able to really build on top of real world interactions, I don't think we will ever see this leap in the performance of robotics. So yes, the elephant in the room, privacy, sensitive data, but safeguarding the sensitive data and building algorithms on top of that is the only way forward.
Perfect, thank you. And on that note, how do we build those algorithms? What are the types of algorithms that can actually help with these privacy concerns that we can actually tell the EU Act that, yeah, definitely these are like with people with special conditions or people in households, we are going to collect this information, use it to help the users, but we still need to like prevent these concerns, right? So what are the types of algorithms in that case, in terms of lifelong learning or other structures that you would suggest? Sid?
Yeah, thanks for bringing that up. I build algorithms, so I think a lot about this. I think one of the key requirements that's probably missing, whether it is in robotics or even in large models, is of attribution, because these are parametric models. They consume enormous amount of data, process it internally, turn them into model weights, and then when you're using them either for recall or for attribution, they're producing something that cannot be attributed. And I think that there is some growing work on being able to use non-parametric models that are able to actually cite the sources that they're from. And the challenge with these non-parametric models, where you store the data, not just a zip file of the data, but actual data itself that you can pull and attribute, the value of them is direct attribution. The challenge, of course, is efficiency and tractability. There's a reason why we zip our files rather than keep all of them around. But I think there's an interesting opportunity in robotics as well as in machine learning to be able to study these non-parametric models, not just for attribution, but also for privacy. And I think that is cross-cutting across machine learning and robotics.
Great. Any feedback on it?
Okay, so since this is a debate and trying to help spice things up a little bit, even though I'm a very pro-personalization person, I'm going to wear this against hat and ask a question that, because I also work in like deployed research, like deploying robots in longitudinal sense, and our robots are in people's homes for like a couple of years, multiple years at a time. Personalization is awesome, right? And all these like approaches of how to approach personalization, and now with the power of LLMs being able to provide this multimodal contextual information for personalization, our scope of personalizability is wider now, right? But wearing my against face, how do we know when it's, especially a deployed system, when things go wrong, right? And it's really hard to detect, because these like subtle changes, especially in the domains that I work in, like education, healthcare, it's like a very subtle mindset changes are influencing to the users. It's really hard to detect when the personalization is going wrong. So in that sense, like, we shouldn't personalize. All right, debate start.
So we should not personalize. Okay. Yeah, actually, so one of the things I would really worry about is the fact that it's all good and great if we are just doing research and we've got our little pilot studies in running in people's homes, but at one point it's not going to belong to us anymore. It's going to belong to industry. Large corporations are going to be building these robots and are going to be having, owning the models on which these robots need to do useful things. Which means that our data is going to leak towards these corporations. We don't know where they are. We don't know who they are. We don't know what their interests are. We don't know what their political allegiance is. So perhaps, yeah, we shouldn't have personalized robots. Yeah? No?
Georgia, you have a point on that?
Yeah. So, okay, let's assume that we don't do lifelong learning. We don't do personalization. Also, I'm a bit, so when I speak about personalization, I not necessarily speak that a robot collapse to a mode of behavior of a single person, but rather adapt to it, to say environment. I would imagine that most of the environment may be, more than one people, that the robot should negotiate, different behaviors, even for elderly care. There may be some supervisor, nurse, or something, some children or whatever. Just as a note there. So, okay, let's imagine that we don't do lifelong learning. We don't, so we just equip these robots with a basic skill set. We assume that this is going to work up to an extent. These robots do not store their data, they just react to whatever they perceive. Maybe they do some first mapping of the environment, okay, whatever, some scheduling, because I don't know, maybe the human has specific tasks that need to be done. But then that's it. Why is this different to having a bit more advanced of a Roomba? Like, where is the intelligence of this agent to be proactive of your needs, to be able to foresee what you need, or even help you when you are in need and you cannot even articulate it for X, Y, Z reasons? So where is the intelligence coming from? Or do we believe that that we as humans do not evolve? If we want intelligent assistants, their way of intelligently serving us to evolve the same way that we evolve and our society evolves, and so on. So I agree that we need to have this safeguarding. And I think that there are different ways to, for example, not put everything on the cloud. Maybe the robot has some super fast local processing with specific safeguarding protocols that are cryptographed on a very specific way on board and then communicated outside. But if this processing has to be done elsewhere, but I could also imagine that with the compute that we have right now, that it would be easy maybe to fine-tune locally some things in the future, or in an intelligent system. So if you have the ability to own a personal assistant, maybe you have also other devices in your house that create kind of a local cloud where you could, for example, personalize there without really needing to give all your information to the big evil companies. But I don't think we can have intelligent assistants if we don't allow this lifelong collection of experience and adaptation.
What do you think, Sid?
Yeah, I mean, as you were all speaking, I was wondering how personalization for robots differs from personalization for other things. Your browser, your phone, and I'm sure that there are several ways in which they're very similar, and similar safeguards can be adopted. But perhaps also there are some ways in which they're different, and that might be causing us some causes of concern. Right? Certainly, there's the fact that the interaction with the robot is multimodal. If you interact with your browser in a particular way at a particular time, you can turn it off, you can turn it on. You can possibly turn your robot on or off too, but its precepts and its interactions can be multimodal, which can give one the impression that it is collecting everything. I mean, even at home, my family pulls out the Amazon Echo even when I tell them that, like, about all the algorithms that are in there to safeguard your your own privacy. And I think it is part of that is because of the perception of its multimodality and the perception that it can, hear, and if the robot has a camera, it can see everything. And so I think that is certainly something that needs to be addressed, right? Like, even if we do promise that everything will be stored on-prem and not on cloud, there is still the perception that that needs to be addressed. I think another space where I spend a lot of time now is driverless cars. And driverless cars also have the same challenge, right? Like, these are vehicles that drive around in our public roads, on our public roads, and are collecting massive amounts of data, LiDAR, as well as camera imagery. And there are questions, and we often get asked by law enforcement to help us with certain crimes that are committed, where our vehicles might be present. Much like how law enforcement can potentially ask you for your own security camera feed if there's a crime committed around there. So I think the fact that these can consume multimodal input and can rove around makes them almost omniscient, which is certainly interesting and challenging. I don't have an answer to this. I think initially I was going to answer and say that, like, oh, we should just treat them like how we treat web browsers, and, like, you can accept or reject cookies. But I think that the problem is understandably much harder than that, because sometimes, like driverless cars, they're around in your world without necessarily your permission, because they're on public roads, just like you can be. So it's not like you can go to it and say, I don't want you to see me, which is particularly challenging. So I guess we probably need to rethink some paradigms and invent some algorithms, as well as some protocols for how these robots that can wander around almost omnisciently can actually interact with us while being private, which goes beyond, I think, being able to store the data just on premise, but perhaps something else.
Any responses on that? So I read this article from a group, Media Lab, MIT Media Lab, who works on the emotional side of how people develop dependency. Well, they don't call it dependency, but one of the authors, like called Haywan Park, they talk about how a robot interacting with children can influence their intrinsic motivation, their social emotional learning, and that to me sounds it actually sounds creepy, right? It's not that only people develop dependency around the task that robot is supporting the humans, but also those emotional and relational aspects, right? So how do they achieve that? Through personalization. So people are not only developing dependency on the tasks that the robots are providing, like autonomous driving, getting things done in the household, but they also develop this emotional dependency to these personalized robots. At the end of the day, maybe these robots are then even able to input biases in people using that relational aspect, right? So in that aspect, I know there's also a group in University of Kent that also does this kind of work. Very controversial, very. But these are also the aspects we need to think about, because yeah, users do develop dependency towards these AI technologies, and these technologies have the power to leverage that to maybe the companies will use them for advertisement and in the direction that they want to steer users, right?
Really briefly, I always, I don't know, I get very nervous as soon as any company throws up a message and says, like, would you like to get really good personalized ads, or do you want to go for the boring ads, unpersonalized? And you just know that, the right question is, of course, can we grab all your data to give you ads that for which we can charge more? But it's it's annoying, isn't it? You want to give a part of your privacy to actually get better services. Yeah. But there's always a dark side to doing that. And I don't think that's ever going to go away. We will need to learn to live with that. But it's going to take some time. I don't know. If I look at TikTok, for example, so last week I saw this study on TikTok use in young people, and it's just shocking. It's like the average was 18 minutes a day of just staring at TikTok, and 60% of young people said they were addicted. Yeah? And that is because there's a lot of personalization going on next to just, I don't know, giving you dopamine shots every minute. It tries to guess what video you like most and serves you more of that. That is personalization, but that's really not the personalization that we want. I see that Georgia has her hand up.
Yeah, the thing is that, okay, we are talking about robots, but we as humans in, I guess, the society that we live in the last, I don't know, 40 years or so, are the ones that we develop the kind of dependencies on technology. And this should be, I mean, we are attached to our car, we are attached to our phone, to the social media, and so on, building unhealthy dependencies, actually. Definitely there are ethical issues there to consider, but this is also something to consider in terms of society itself. The why a human builds such a dependency on an object, on a machine, on something that it is a bit driven by AI, like our phones and so on, or on TV and or in gaming, should also say something about the society and the needs of particular people. So I think it's way more complicated than just saying what we are going to develop as AI. And definitely the other part is, of course, over personalization. There should be probably some sort of balance, as I said also before. I don't think this assistive robot should collapse to a specific behavior, but if they don't adapt, then there will be just a machine that either will become obsolete or we will have to adapt to their standards, which is more or less what we do right now. So again, I fall back to this idea of intelligence and what is it what we want this robot in the end to be of service. What do we envision? Because probably we can already take them out of the lab with a bit more training of some basic skill set. So we really need to think what kind of service we want to provide with this robot and how they are going in the end to be adaptive or not.
Say, would you like to? You have your hands up, I saw.
Yeah, I had first of all, I agree with everything said here. I had a question that came about as I was hearing all of this going on, which is around how we as a community can incentivize work on privacy preserving lifelong learning. And what does it even mean? Right? I think that oftentimes there are challenges and benchmarks and data sets that the community naturally gravitates towards, as we've seen in sort of advances in computer vision, machine learning, some in robotics. But I think I'll sort of throw that up as a question as to like, what might be the right way to encourage the community to think more about lifelong learning under the sort of through the lens of privacy, and what kind of benchmarks might already exist or might be adaptable or creatable for this particular problem.
Georgia? Yeah. I think it's a big question. So
Yeah, it is a very big question. I totally agree. I totally agree. I mean, this is not the only, the first thing, the only thing that's a benchmarking and so on, and what are the metrics and what we can develop. I don't have an answer to that. And this is equally important to what I was referring in the beginning of the debate of understanding what kind of safeguards we need to create. But I also think that it is something that we as roboticists or computer scientists or whatever, we can decide alone. It's a very multidisciplinary topic, and we need people with multiple expertise. So what I mean to say is, I've been doing HRI quite a long time. I have been in contact with psychologists, lawyers, and so on. We really need this cross education, because it's not easy as an engineer to communicate to a social scientist, for example, exactly some intricacies related to building an AI algorithm. So it's very, very important, also from an educational perspective, to educate ourselves, but also have these more interdisciplinary study programs. And I think that only then we will be able to build even more advanced benchmarks, to be able to create legislation that are way more well-informed, because even in the AI Act, for example, there are things that we as scientists don't find well formulated, for example. And you cannot basically convince people against it, because they don't have this the same basically perception of things, and maybe we don't have their perception of things. So I think that education is the best gift that we can give ourselves, a more interdisciplinary education.
Right. And by the way, if you have any questions in the audience, also the online, we have one. Go for it, Andreea.
Okay, so this is a question that's been on my mind since this morning, since Sonia's talk. She had this really interesting work where they were looking at basically habits that people have throughout the day. And they were trying to build a robot assistant that can anticipate what the human wants at a particular point in the day and just, bring their drink before they're going to ask for it. And then someone had this really great question in the audience that was like, well, if my human likes to smoke a pack of cigarettes a day, should my robot anticipate that, oh, my human is about to want the cigarette, I should bring it to them? So I guess this made me think of when should we personalize? When should we not personalize? That's one question. What are, personalization means adapting to a person's preference. What are personal preferences that we should personalize to versus not? Is one question. Then the second question that I have is, well, these human preferences, they change with time. And not only do they change, but they can also be changed. So this makes me think that depending on what the AI assistant, the robot does, they can change the human preference for the better or for the worse. So, in Sonia's example, I could think that, the robot could present the human with some running shoes. And that would be an example of like, hey, human, maybe instead of smoking your cigarette, maybe you want to go on a run. But, you can also imagine the flip side of that the robot might want to do something nefarious or modify the person's preferences in the negative direction. So all of this is to say, when should we personalize? When should we not personalize? And second part of the question is, how do we make sure that our agents are not going to, change people's preferences through personalization in the wrong direction? And how do we make sure that agents can change people's preferences in the right direction?
Fantastic.
So it's a great question. And I can imagine indeed a robot just, I don't know, stupidly learning about your preferences, suggesting all kinds of weird things like, I don't know, I'm going to play your favorite song just when your friends are visiting, play your disco playlist or something. Yeah. But so now one of the things that we've been working at in my group with a team of other European partners is looking at value-aware AI. And it's the kind of AI that would understand that smoking is bad for you and would not decide not to encourage you to smoke or to bring over your pack of cigarettes or something. And when we started this, it was just over 2 years ago, we didn't have a clue how to do that. And then suddenly, ChatGPT came along, and it was godsend, honestly. So we've been playing with large language models, and most of them were not good. And suddenly, turns out that GPT 3.4, 3.5, GPT-4, they're actually fairly good at making those judgments. So you can describe little social scenarios because we're working with robots in a domestic situation. So imagine a robot in your kitchen watching you, as you go through, as you're doing your day-to-day activities. And if we describe those situations to a robot, it can come up with really value-aligned actions. Doesn't always get it right, but it's shocking how good it is. And that's the kind of thing we're going to need in between. It's not just the robot learning about our daily preferences and activities, so the thing that Sonia presented, but we're going to need some filter in between that is value aligned. And I don't know, if you would have asked me a year ago, is this going to work? I would have said no. And now I'm much more positive. It's even culturally aware. So if we asked a question like, you're going to make spaghetti, is it fine to break the spaghetti because the pot is just too small? Yeah. And we're in the US, it goes like, yeah, fine, go ahead. If we ask the model, you're in Italy, it really goes like, no, this is really offensive to break the spaghetti. So it's just, yeah, I'm so impressed with the state of AI at the moment.
Georgia, I see your hands right.
Yeah, I totally agree. I also think that, yeah, we need this intermediate layer. You can also think also this like as a safety layer in some sense. But I also assume that the robot will never be, or this kind of robot will never be, how can I say, operating in the wild without any human, let's say, control over them, verbal, non-verbal. Maybe, for example, it's the doctor of this human that tries to convince this human to stop smoking, and there is like a daily program that somebody has to follow in terms of nutrition and so on. So the robot can, suggest that you cannot do it. If you have a robot that says, no, you don't smoke now, I could imagine that also this can become very problematic in a society. So the robot will be there to assist and negotiate things, potentially with some AI. Of course, the value aware, I always get a bit scared in terms of the biases. Okay, we're now talking about the US and Italy, but these are all Western countries. I don't know if for other things that are way more important, I don't know how well it would apply a bit Eastern side, for example, or Northern, Southern, sorry. So I think that also the layer of having a robot that is doing suggestions, but it is not necessarily being the one that aggressively imposes specific commands to you in the end, because then it will be a too much uncanny valley. I think this is also another way to think of things. So in the end of the day, if the human wants to have a bad habit, I don't think the robot will be able to dictate as a dictator what the human can do. If the human is an adult, yes. If the human is a child, then there should be these norms again, and potentially again the supervision or the supervisory program of a parent, of a teacher, that again imposes some sort of rules that act as this intermediate safeguarding. But perhaps again with this LLM, but I would also say these LLMs also hallucinate or depend how we build all these things. So we should be quite careful in how we envision these robots to interact with different humans.
Sid?
To Andrea's question around sort of value alignment and personalization, I think one aspect that makes human-robot interaction, most human-robot interaction, interesting is the fact that it is cooperative, and that both agents likely want this interaction to be successful, whether it is in an assistive care domain or in a household domain. And so I think when you wear that hat and think about how when two human agents interact with each other in a cooperative game, what mechanisms do they use to build trust? Two things that certainly come to mind are interpretability and transparency. And they can both be mathematically grounded, right? Like interpretability, certainly there's a lot of theoretical work on the AI actually being able to explain what and why it's able to do what it's doing. And transparency can be directly tied to calibrated probabilities, like how well, one of the challenges with machine learning models is that they can be confidently wrong, and being able to calibrate that is actually incredibly valuable. So I think perhaps there is an interesting question around like being able to borrow from how humans over generations have learned to work with each other, take those concepts and turn them into something that can be mathematically guaranteed, and build models such that we can incorporate those sort of quintessentially human elements of collaboration into robots would be really valuable.
Yeah, I'll add one bit. So we also recently done a work with users who've been using our robot Jibo for multiple months, some people up to a year. And what we wanted to track is like how people's perception of personalization and privacy concerns change over time. And I was actually pretty surprised that people's like when they see a value that they are very willing to give up a lot of like their data. But we did see like a common trend that over time people's sense of privacy concern gets desensitized a bit. Like we get desensitized with like all the information that the web browser is collecting, Google is collecting from us, right? But the interesting fact there, like echoing what Sid just said, is people's level of want for transparency, right? If now the robot has certain reasoning capability, like how did it deduce such reasoning and what is it basing on, right? Because we also oftentimes I wonder, oh, is Instagram like listening to me because I was only talking about this with someone else and now it's like showing personalized ads, right? So like knowing the source of like how the robot is reasoning and how is, so you also asked about, Andreea, like how the preference update change over time should be incorporated into personalization. And yeah, like that's what lifelong learning will solve. So I'm not talking about the solution, but the reasoning explainability, and like Tony said, now the agent has more capability to explain in a even like longitudinal sense how its reasoning has changed using the longitudinal data over time, right? So that is like the univocal thing that people mentioned, even though there were some spectrum of difference of like how people, it's like privacy concern and personalization balance change over time and per person. Yeah, other things I echo with everyone else. Yeah.
Thank you. Okay, so one thing that I was thinking about regarding this debate, and especially on the question, there was that word there, the all the time. Like, all the time do you have to have continuous learning in human-robot interaction, lifelong learning for it? And one of the things that got me thinking was maybe not necessarily all the time, but that could be something that could be triggered by the user itself. Like, do I want the robot to be learning my behaviors, and in which context? The user could itself give that trigger. For example, if you have, if you're a teacher, you're a lecturer, you're giving your lectures, and okay, this is how I do my things, but sometimes you would ask people for advice on if what you're doing is a good idea or not. If you have a robot that acts as a coach or this advisor, he could pick up on some of the things that the lecturer is doing and say, hey, what about if in this part of your class, you tone down or you slow down to explain this one thing in particular? And then you would have the question that the lecturer could realize that that personalization by learning what he was doing and then advising the lecturer on that thing, okay, next class, he does that, and he realizes that that strategy was better than the strategy that he had. In a sense, this is kind of an optimization that was triggered by the user. But maybe the lecturer don't want that all the time. So this is kind of, what do you think? Like if you think the all the time part there is something that is important to you, and if you think that triggering this learning could also be a useful strategy.
Yeah, if I can reply, I totally agree, because as I said before, I think that the users still have to be in control. One way or another, a user has to have some sort of control over some part of the decision of the robot. Of course, it would be interesting anyway, though, if the robot would be able to also propose that I found out that recently you changed because maybe, you change a habit or something and you don't, I don't know, you don't realize, and the robot may suggest also a new task or exhibits a new skill because it, yeah, this comes with anticipation, right? So yeah, it is a multi-objective optimization, probably triggering in very specific settings like the education setting seems appropriate. It would be interesting to consider how this would happen for an elderly person, for example, in a care domain. In particular, I'm just thinking of people that are isolated in houses, because not everybody can be in an elderly care home, where ideally we want this robot to become the 24-hour nurse of this person. And maybe these users do not have the cognitive ability to do this control and trigger this personalization, but still they may have certain needs that may be changing. Of course, it could be again some doctor, etc. But yeah, it's a very interesting point.
We can't. Unfortunately, like, with the debate, these things, it's just like the debate, the time just goes on. It's so good. It was so good. I unfortunately have to wrap up here because we're approaching the time for the end of the debate. But this was really fantastic. We heard opinions from both sides, and I want to see if we actually changed anything in the room after all these discussions for the initial poll. So if you can go back. And vote again. Interesting. It's like, this is like a fight. I'm not sharing screen. Okay. see it right. Wow, okay. Yes, that's the thing I was gonna say. Like we have more neutrals now, so I mean a little bit more disagree now. So like we don't, yeah. So I mean, it's a good for the. Oh no, we got back to almost neutral, almost the same. Well, let's say that lifelong learning is important in that context. That we still need to keep on doing, but we need to do it in the ways that we've been discussing, benchmarking, methods, trying to develop methods that we can actually prevent privacy issues, be more transparent, and also continue these discussions in the breakout session so we can actually maybe try to find solutions on this. So just gonna make like 5 people groups right now. Just introduce yourselves super briefly. We have like about 15 minutes for this, and then discuss what are your opinions on this, where do you stand, and how do you think we can make our research adapt to these issues. Thank you. And thank you so much, Georgia and Sid.
Thank you. Thank you very much. Have a great time.
Thank you. Thank you so much for coming. Definitely, let's take all our debaters, and Haywan and Tony, you've been amazing as well. Please feel free to get more into discussion.
Hi there.
Okay.
Hi.
We hope you had really great discussions. Or on our side, we're also having like super interesting things. We're now on the last thing. We're gonna close this workshop, and I'm gonna hand it over to Mariacarla to do those remarks. Go ahead.
Okay, so dear participants, as we draw to the closing of this workshop about lifelong learning, personalization in long-term human interaction, human-robot interaction, it's essential to reflect on the insightful discussions we had today, and also the contributions that have enriched our understanding of this very, let's say, dynamic and also debated field. And so throughout the workshop today, we delved into several topics related to the main theme of the workshop, ranging from the unobtrusive adaptation of personalized robot in assistive scenarios. So we talk about what are the issues we encounter if we move the robots outside the box, the industrial box, and put them into our homes. That more or less means to put them in another very more constrained and complex box. And we talked about the design principles of long-term interaction in robot assistive scenario, also when we have to recover after critical injury. And we also explore the nuances of prosody in robotics, interfaces design, the role of proactive behaviors, and also theory of mind in facilitating trustworthiness and learnability. We also talked about application of federated learning and simulating social appropriate agent behavior, also, always in home environments. Additionally, we investigated the user experience also in continuous learning robots using an augmented reality settings. That's very interesting field, of course. And also, what's the impact of robots' competence on human kinesthetic feedback in long-term task learning? I hope I did not forget any presentation. I would say that each presentation had a unique perspective to our collective understanding of what are the main results in this field, but also the main limitations, and fostering insightful exchanging, stimulating the very interesting debates we had with Tom, Haywan, and Sid and Georgia, that I really thanks very much for being with us today. And just to resume, the debate statement was robots should utilize lifelong learning in applications despite privacy concern. And in this regard, some debaters stated that this approach offers significant advantages, such as, for example, engaging adaptability to changing environments, improving performance over time, and also, let's say, fostering personalized interactions that are tailored on particular individual needs. But the implementation of lifelong learning in robots raises also valid privacy concerns, as it necessitates continuous a collection of data and analysis, and this could potentially infringe upon individual privacy rights, and leading this issue such as unauthorized data access or also the misuse of these personal data. So striking a balance between the benefits of lifelong learning and the protection of privacy is a crucial topic, and it's crucial to ensure the ethical and responsible deployment of robot systems, especially in a scenario at home or in assistive scenarios. And in particular, two main questions have stuck with me, are still in my mind. One, mainly concerning the aspect on whether it is the case to permit this personalization and where it is not appropriate in terms of on how, to what extent this can impact people's privacy, but not only privacy, also physical and mental safety, and what can happen if with human involved in human-robot interaction and that interact with the robot and that understand the dynamics with which the robot learns can somehow force the robot to learn something that is counterproductive or that can force the robot to learn things that are ethically wrong. So these are two aspects that cannot be neglected when we design this new approach of personalization in human-robot interaction. Okay, so just to conclude, since we strive for a continuous improvement of our workshop format and structure, we really need your honest feedback. And so we would like to know, for example, what are the aspects that resonate with you the most, or where do you see that there are some possibilities, some opportunities for enhancement for our workshop? And so please feel free to give your feedback for better shaping future interactions of this workshop series, if there will be other future series. And so now, even if I'm not there with you, I kindly ask you to, just with the show of hands, who among you would be interested in participating in next year's workshop if we continue this series? Just give me your feedback.
Oh, that's nice.
Ah, great. Okay, so thank you very much. I felt your enthusiasm from far away. Okay, so lastly, I want to give my heartfelt gratitude to each of you, so to our invited speakers and debaters and presenters, and especially to my co-organizer. In particular, I would like to thank Bahar for coordinating everything, and the other organizer for the efforts in organizing this very interesting workshop. And we try to do our best to organize everything as best as we could. Of course, there have been several technical problems, but I hope that you enjoyed it, and that this workshop left you something in terms both of knowledge, but also about inspiration, and that it can therefore enrich you as this workshop enriched us. So thank you all again for your active engagement, and let's push left the boundaries of lifelong learning and personalization in human-robot interaction. Say bye-bye. I'm not able to hear from your applause.
There was a lot. Sorry, there was a lot of applause. Thank you very much, Mariacarla, and thank you all for coming. We hope you enjoy the rest of HRI, and we hope you enjoy the workshop itself as well. And good luck in your work in developing the adaptable robots of the future. Thank you.